Hello there, and welcome to Science for Sleep, where curiosity gets comfortable and big questions are allowed to unfold at an unhurried pace. Tonight, we're turning our attention towards something that sounds simple on the surface and impossibly large the moment you pause to think about it. We're going to talk about why humans cannot travel even 1 light year. That distance, just 1 light year, sounds modest in a universe filled with billions of galaxies. It sounds like the sort of number that should be conquerable with enough determination, enough funding, and perhaps a slightly overconfident engineer. After all, we've crossed oceans, climbed mountains, split the atom, and placed footprints on the moon. Surely 1 light year cannot be that unreasonable, and yet it is. Before we go any further, I'd love to know something. Where in the world are you listening from tonight? Are you wrapped in a blanket somewhere quiet? Perhaps in a city glowing with streetlights, or in a countryside where the sky's dark enough to show you the stars we're about to discuss. And what time is it where you are right now? Early evening? Deep night? Somewhere in between? It feels fitting, doesn't it, to ask about time when we're about to talk about distances measured by it. If you find this kind of exploration soothing, or if it gives your thoughts something gentle to wander through before sleep, I'd be quietly grateful if you liked the video, maybe subscribed, and shared this calm corner of science with someone else who might enjoy it. It helps this small orbit of curiosity continue spinning. Now, let's settle into the question itself. A light year is not a measure of time, even though it sounds like one. It's a measure of distance. Specifically, it is the distance light travels in 1 year. Light moves at about 300,000 kilometers per second. That's fast enough to circle Earth more than 7 times in a single second. It's fast enough to travel from the Earth to the Moon in just over a second. It's fast enough that, in everyday life, we treat it as instantaneous. But give that speed an entire year, and the number becomes something else entirely. In 1 year, light travels roughly 9.46 trillion kilometers. Trillion. That's a 1 followed by 12 zeros. If you try to drive that distance in a car, even without stopping for fuel or snacks or the occasional existential crisis, you would need millions of years. If you tried to fly it in a passenger jet, you would need even longer than recorded human history. 1 light year is enormous, and here's the first quiet realization that starts to shift things into perspective. The nearest star beyond our Sun, Proxima Centauri, is about 4.24 light years away. Not 40, not 400, just over 4. That's our closest neighbour in the vast stellar landscape, and we cannot even travel 1. It's tempting to imagine that this is simply a matter of better technology. We often assume that limitations are temporary. After all, there was a time when crossing the Atlantic Ocean took months and was dangerous. There was a time when reaching orbit seemed impossible. Now we do these things routinely. So maybe, we tell ourselves, interstellar travel is simply the next step. Yet when we examine the physics calmly and carefully, something different emerges. Let's begin with speed. The fastest object humans have ever built is not a spaceship designed for deep space exploration. It's a solar probe. NASA's Parker solar probe, at its peak speed during close passes around the Sun, travels at about 700,000 kilometers per hour. That sounds extraordinary, and it is. It's fast enough to go from New York to London in less than a minute. It's fast enough that any terrestrial speed limit becomes almost comical by comparison. But even at that astonishing speed, how long would it take to travel 1 light year? If you did the math, and we will, you'd find that it would take over 1,500 years to travel just a single light year at that speed. And that's assuming you could maintain that velocity continuously in the right direction, without slowing down, without course corrections, without fuel limitations. 1,500 years. That's longer than the time between us and the fall of the Roman Empire. It's longer than the age of most nations. It's far beyond any human lifespan. It's not just impractical, it's incompatible with how human biology works, and that's using the fastest object we've ever built. You might think, well then we just need to go faster. That's where the next problem appears. As objects approach the speed of light, the energy required to accelerate them increases dramatically. Not linearly, not gently. It increases in a way that becomes almost absurd. According to Einstein's theory of special relativity, as you get closer to light speed, your mass effectively increases from the perspective of an outside observer. That means pushing the spacecraft even faster requires more and more energy for smaller and smaller gains in speed. To reach 10% of the speed of light would require an amount of energy comparable to the total annual energy consumption of humanity, multiplied many times over for a single spacecraft. To reach 50% of light speed would require staggering amounts of energy that we do not currently have the ability to produce, store, or manage safely, and we haven't even discussed slowing down at the destination. Because if you accelerate halfway to your target, you must decelerate for the other half. That doubles the energy requirement. The universe does not provide free braking. Then there is fuel. Rockets work by throwing mass in one direction to move in the other. That means the more fuel you carry, the heavier you are. The heavier you are, the more fuel you need to move that mass. The more fuel you add, the heavier you become again. This relationship is described by something called the rocket equation, and it is deeply unforgiving. To accelerate a spacecraft carrying humans to even a fraction of light speed using conventional chemical rockets would require a fuel mass larger than the spacecraft by factors that quickly become unrealistic. To achieve meaningful fractions of light speed, you would need fuel masses larger than entire mountains, larger than small asteroids, possibly larger than planets, and we are still only discussing 1 light year. Another quiet complication waits in the background. Space is not empty. Interstellar space is extraordinarily sparse, but at high velocities, even tiny particles become dangerous. A speck of dust travelling at a significant fraction of the speed of light relative to your spacecraft would strike with the energy of an explosive projectile. Shielding against such impacts would require additional mass. Additional mass requires more energy to accelerate. More energy requires more fuel. More fuel increases mass again. The cycle continues. Meanwhile, the human body is not designed for centuries of confinement. Even long-duration missions aboard the International Space Station produce measurable effects. Muscle atrophy, bone density loss, radiation exposure, psychological stress. Those missions last months, sometimes a year. They do not last centuries. Even if you imagined a multi-generation spacecraft where children are born and raised during the voyage, the engineering challenges multiply. You would need a fully closed ecological life support system that functions flawlessly for hundreds of years. You would need governance systems, social stability, protection from cosmic radiation, reliable maintenance infrastructure, and solutions to problems we cannot even predict yet. And remember, this is just to travel 1 light year. Not to arrive at a habitable planet, not to colonize, just to cover the distance. There's something quietly humbling about that. Human civilization feels vast to us. Our cities are enormous. Our networks span the globe. Our satellites circle Earth constantly. We stream information across continents in milliseconds. It can create the illusion that we have conquered distance. But cosmic distance is different. When we look up at the stars, they seem close together. They form patterns, constellations, familiar shapes. It feels like you could reach out and almost touch them. Yet those points of light are separated by trillions upon trillions of kilometers. Our intuition struggles with such scales. 1 million is hard enough to visualize. 1 billion stretches the mind. 1 trillion becomes almost abstract. A light year, at nearly 10 trillion kilometers, exists far beyond anything our daily experience prepares us to comprehend. Still, the dream persists. Science fiction has taught us to imagine warp drives, hyperspace, wormholes. It has trained our imaginations to accept that distance is merely a narrative obstacle. Push a button, engage the engines, and stars slide past like streetlights seen from a moving train. The real universe is less accommodating. Physics does not forbid interstellar travel entirely. It simply makes it extraordinarily difficult. It demands enormous energy. It imposes strict speed limits. It punishes mass. It stretches time in strange ways as velocities increase. It introduces radiation and collision hazards. It requires life support systems that function for durations longer than recorded history. And so, for now, even 1 light year remains beyond our reach. There's something interesting about that boundary. We live on a planet where crossing oceans once seemed impossible, where flight once seemed absurd, where reaching orbit once seemed unimaginable. Yet each of those milestones was achieved within environments governed by gravity, atmosphere and distances measured in thousands or millions of meters, not trillions of kilometers. The jump from planetary travel to interstellar travel is not like upgrading from a propeller plane to a jet. It's not a gradual improvement. It's a leap across a gulf so wide that even our boldest engineering struggles to span it. Sometimes people ask whether future technology will solve this, perhaps with nuclear propulsion, perhaps with antimatter engines, perhaps with light sails driven by powerful lasers. These concepts are being studied. Some are plausible in theory, but each carries its own immense engineering challenges, energy requirements, and practical limitations. And even if we could accelerate a small probe to a significant fraction of light speed, carrying humans remains an entirely different problem. Humans are fragile. We require air, water, food, psychological stability, protection from radiation, and complex social systems. Machines can endure far more. They can travel alone. They can transmit data back across the darkness. Maybe that is the key difference. It might be that the first travellers to cross even a fraction of a light year are not people at all. They are machines, probes, artificial intelligence systems designed to survive what biology cannot. That idea changes the tone of the question slightly. Instead of asking why humans cannot travel 1 light year, we might begin to ask whether we need to. Because even from here, even from Earth, we are learning. Telescopes allow us to detect exoplanets dozens or hundreds of light years away. We analyse the chemical composition of their atmospheres. We measure their sizes and orbits. We search for hints of habitability. We have not crossed the gulf physically, yet we are reaching across it with light, mathematics, and patience. Still, there is something deeply human about wanting to go. We evolved as explorers. We spread across continents. We crossed land bridges and oceans. We climbed mountains not because they were easy, but because they were there. That instinct does not disappear simply because the distances become inconveniently astronomical. At the same time, the universe gently reminds us of scale. It reminds us that our achievements, remarkable as they are, exist within a narrow band of physical possibility. It reminds us that energy is not infinite, that speed has limits, that biology has constraints, and perhaps that's not discouraging, perhaps it's grounding. At first glance, 1 light year sounds almost modest. Just 1, not dozens, not hundreds, not the kind of number that usually triggers alarm bells in the human mind. We are very good at coping with small numbers. 1 apple, 1 hour, 1 mile, 1 more episode. These are comfortable ideas, familiar ideas. So when someone says 1 light year, the word 1 does a lot of quiet work, soothing the imagination before it has time to panic. But the comfort doesn't last long, because the moment you pause and ask what that distance actually represents, the scale begins to slip out of reach. Not dramatically, not all at once. It does so slowly, the way a shoreline recedes when the tide goes out, leaving you suddenly aware of how far the water once seemed to be. A light year is the distance light travels in 1 year. That sentence is accurate, simple, and deeply misleading if taken casually. Light feels fast to us in an almost abstract way. Turn on a lamp and the room is instantly bright. Look at the moon and you don't feel the 1-second delay. Even sunlight, which takes a little over 8 minutes to reach Earth, arrives so predictably that we forget it was ever travelling at all. Light feels immediate, and that sense of immediacy tricks us. Light moves at roughly 300,000 kilometers per second. That number already stretches intuition, but seconds are small, slippery units. It's hard to hold on to them, so let's slow the universe down just a little and build the distance piece by piece. In 1 second, light travels around Earth more than 7 times. In 1 minute, it covers about 18 million kilometers. In 1 hour, it crosses over 1 billion kilometers. In 1 day, it spans more than 25 billion kilometers. At this point, we have already passed the distance from Earth to the Sun more than 170 times. Now let that continue, without interruption, for an entire year. No pauses, no slowing down, no obstacles, just steady motion at the fastest speed anything can have. By the end of that year, light has travelled about 9.46 trillion kilometers. That's the distance we're casually calling 1. The problem isn't that humans don't know this number, it's that our minds don't know what to do with it. Trillions are not part of everyday thinking. They don't appear in grocery shopping, daily commutes, or household budgets. Even national economies, which often deal in billions, rarely touch trillions in a way that feels tangible to individuals. So the brain compresses, it rounds off, it shrugs and says, very far, and moves on. But very far is doing far too much work here. To understand why 1 light year is such an obstacle, it helps to compare it to distances we think we understand. Earth is about 12,700 kilometers wide. Flying around the planet once feels like a long journey, but it's something humans have done tens of millions of times. The distance from Earth to the Moon is about 384,000 kilometers. That was once an unimaginable gap. Now it's something we crossed with 1960s technology. The distance from Earth to the Sun is about 150 million kilometers. That's large enough to be difficult to picture, but still within the same general category. Spacecraft have crossed it many times. Probes do it routinely. Now here's the uncomfortable part. 1 light year is about 63,000 times farther than the distance from Earth to the Sun. Not farther in a poetic sense. Not farther in a wow, that's big sense. Literally tens of thousands of times farther. Imagine stacking the Earth-Sun distance end to end, again and again, until you've done it more than 60,000 times. That is still only 1 light year, and our nearest neighbouring star system is more than 4 of those away. This is where the word small quietly breaks down. Astronomers often use light years because the universe forces their hand. Kilometres become unwieldy very quickly. When you're talking about distances between stars, writing out the full numbers becomes impractical. Light years compress the math into something readable, something discussable. But readable is not the same as reachable. The human body evolved on a planet where distances are measured in steps, days, or seasons. Even our longest migrations, carried out over thousands of years, unfolded across continents, not across voids. Our sense of distance is tied to effort, not emptiness. A mountain feels far because climbing it is hard. An ocean feels vast because crossing it is dangerous. Space introduces a different kind of far. Between stars there is almost nothing. No air, no landmarks, no intermediate stops. Just a thin scattering of particles and radiation stretched across trillions of kilometers. When you travel across a continent, every kilometer brings you closer to something. A tree, a river, a village. When you travel through interstellar space, kilometre after kilometre passes with nothing changing at all. That sameness matters, because distance is not just about how far you must go, it's about how long you must endure the journey. At human scales, we tolerate long trips because they end within a lifetime. A long flight takes hours, a long voyage takes months. Even the longest human expeditions, measured in years, still fit inside a single biography. People can prepare for them. They can imagine themselves at the destination. A journey that takes centuries breaks that mental model entirely. If you were to board a spacecraft travelling at speeds comparable to our fastest probes, you would not arrive. Your children would not arrive. Your grandchildren would not arrive. Entire civilizations could rise and fall while the spacecraft continued on, unchanged, carrying a crew long since turned to history. That is not a journey in the human sense. It is a process that outlasts individuals, cultures, and possibly even languages. And this is still assuming something very generous. It assumes constant speed. It assumes no failures. It assumes no need to stop, turn, repair, or adjust course. It assumes a level of technological reliability that we have never achieved over even a few decades, let alone centuries. The scale problem doesn't just affect travel time, it affects communication. If you are 1 light year away from Earth, any message you send takes 1 year to arrive. Any reply takes another year to come back. Conversations become impossible. Instructions arrive outdated. Emergencies unfold alone. At 4 light years, which is the distance to the nearest star, that delay becomes 8 years round trip. Ask a question, and the answer arrives almost a decade later. By then, the situation that prompted the question may no longer exist. This isolation changes the nature of exploration. It removes the safety net of real-time guidance. It means that anything that goes wrong must be handled locally, with no help coming in time. Again, this might sound manageable in theory. After all, explorers throughout history have operated far from home. Ships crossed oceans without instant communication. Expeditions vanished into unknown lands. But those journeys still existed within the same planet, under the same sky, governed by the same day-night cycle and the same biological rhythms. They were distant, but not disconnected from the rest of humanity and time itself. Interstellar distance separates not just space, but eras. Another subtle problem hides inside the number as well. Energy. Distance translates directly into energy requirements, because moving something farther, especially faster, costs more. Every additional kilometre requires propulsion. Every additional year requires life support. Every additional system adds mass, which then increases the energy needed to move that mass. When distances are small, these relationships feel manageable. When distances reach trillions of kilometres, they dominate every decision. Even if you imagine an ideal engine, one that converts energy to motion with near-perfect efficiency, you still face the reality that energy must come from somewhere. It must be generated, stored, and controlled. On Earth, we rely on vast infrastructures to do this: power plants, grids, fuel supply chains, maintenance crews. A spacecraft heading toward a star has none of that. It carries everything with it. And the farther it goes, the more unforgiving the accounting becomes. The universe does not offer shortcuts in empty space. There are no downhill stretches, no tailwinds waiting between stars. Motion must be paid for continuously, either with fuel or with clever physics that still obeys conservation laws. When people hear 1 light year, they often imagine a line drawn on a map of space, a straight path from here to there, but space is not a map in that sense. It's an environment where every metre travelled requires justification, where every additional second of motion increases exposure to radiation, where every added kilogram compounds the challenge. Even slowing down becomes part of the distance problem. If you travel fast enough to make 1 light year feasible within a human lifetime, you must also slow down at the end. Otherwise, you simply fly past your destination and continue into the darkness. Deceleration requires energy too, often as much as acceleration, sometimes more. That means the distance effectively doubles in energetic terms, half the journey speeding up, half slowing down, both equally demanding. At this point, the word 1 has completely lost its reassuring power. It becomes clear that 1 light year is not a step, it's a wall, a boundary between the kind of exploration humans are adapted for and a kind we are not. This does not mean the distance is meaningless. Quite the opposite. Astronomers use light years precisely because they reflect how the universe actually behaves. Light is the fastest thing there is, Using its travel distance as a ruler makes sense at cosmic scales. But rulers are not ladders. Measuring a distance does not imply the ability to cross it, and this is where expectations shaped by fiction quietly clash with physics. Stories often treat space as a backdrop, not a barrier. Ships move between stars as easily as planes move between cities. The distances exist, but they do not dominate the narrative. Reality insists otherwise. In reality, distance is the story. Everything else, speed, fuel, time, biology, communication, radiation, flows from it. Once you accept just how far 1 light-year truly is, many other questions begin to answer themselves. Why we rely on telescopes instead of ships. Why probes are favoured over crews. Why discussions of interstellar travel often drift towards speculation rather than engineering. The scale alone forces caution, and yet humans keep asking the question. Not because it's practical, but because it reveals something important about our place in the universe. We are a species that notices distances and wonders whether they can be crossed. Even when the answer appears to be no, at least for now, the act of asking reshapes how we understand ourselves. It reminds us that space is not empty in the way a room is empty. It is empty in a way that stretches patience, energy, and life itself. It reminds us that our planet, small as it is, exists in a neighbourhood where even the nearest neighbour is unimaginably far away. As this begins to sink in, another realization quietly follows. Distance is not the only barrier. It is simply the first one. Once you move past it, others appear, layered one on top of another, each reinforcing the same conclusion from a different angle. When we talk about a light year, it's easy to let the discussion stay comfortably abstract. Numbers, distances, speeds, diagrams drawn on whiteboards or rendered in simulations. All of that keeps the problem safely mathematical, clean, impersonal. But the moment you ask what a light year actually means for a human body, the conversation changes tone. Because a human body is not abstract. It is warm, it is wet, it is fragile. It depends on balance, repair, rhythm, and an environment that quietly supports it without much complaint. It evolved under a specific sky, bathed in a specific kind of sunlight, protected by a magnetic field, and a thick atmosphere that does an enormous amount of invisible work every second. A light year does not care about any of that. To understand why travelling even 1 light year is such a problem for humans, you have to stop thinking like an engineer for a moment and start thinking like a biologist. Or perhaps more honestly, like a physician tasked with keeping someone alive in conditions they were never meant to experience, for longer than they were ever meant to endure. Start with time, because time is the first quiet pressure applied to the body. At speeds we can realistically achieve with current or near-future technology, travelling 1 light year takes centuries. Even optimistic concepts that push far beyond chemical rockets still struggle to bring that number down below many decades. That immediately places the journey outside the bounds of a single human lifespan. The human body is not designed to be paused. It is designed to age. Cells divide. DNA accumulates errors. Tissues wear down. Bones lose density. Muscles weaken if they are not used constantly. The immune system changes over time. The brain itself, resilient as it is, gradually shifts in structure and chemistry. Even under ideal conditions on Earth, aging is unavoidable. In space, it accelerates. We already know this from astronauts who spend extended periods aboard the International Space Station. Missions lasting 6 months to a year produce measurable losses in bone density and muscle mass, even with rigorous daily exercise. The cardiovascular system adapts in ways that must be reversed upon return to Earth. Vision can be altered, fluid distribution changes, sleep cycles are disrupted, immune responses are modified. These effects occur in low Earth orbit, just a few hundred kilometers above the planet, while still partially shielded by Earth's magnetic field, and with constant resupply, medical monitoring, and communication. Now stretch that environment to decades or centuries. The human skeleton depends on gravity to maintain its strength. Without it, Bones gradually release calcium and other minerals, becoming weaker and more brittle. Even if artificial gravity were generated through rotation, which introduces its own complications, maintaining a perfectly stable, Earth-like gravitational environment for centuries would be a monumental engineering challenge. Muscles tell a similar story. They adapt to the loads placed on them, reduce those loads, and muscle tissue is broken down to conserve energy. Over long periods, this leads to severe weakness. Exercise helps, but exercise itself requires space, equipment, energy, and motivation, all sustained flawlessly over generations. Then there is radiation. Earth is wrapped in layers of protection. The atmosphere absorbs high-energy particles. The magnetic field deflects charged radiation from the sun and from distant cosmic sources. On the surface, we're largely insulated from the constant bombardment happening above our heads. In deep space, that protection disappears. Outside Earth's magnetic bubble, the human body is exposed to cosmic rays, high-energy particles accelerated by supernovae and other violent events across the galaxy. These particles can penetrate spacecraft hulls, pass through tissues, and damage DNA directly. Over time, this increases the risk of cancer, neurological damage, and other degenerative conditions. Radiation shielding helps, but shielding is heavy. Thick layers of water, metal, or specialized materials can reduce exposure, but every kilogram added increases the energy needed to accelerate the spacecraft. The shielding must also last for the entire journey without degrading, cracking, or becoming compromised. Even with shielding, some radiation gets through. Over centuries, even low levels accumulate. The body's repair mechanisms can only do so much. The brain is especially sensitive. Neurons do not regenerate easily. Subtle damage can accumulate quietly, affecting cognition, memory, mood, and personality. Over long durations, this becomes not just a medical issue but a social one. Which brings us to psychology. Human beings are social animals. Our mental health depends on interaction, novelty, purpose, and a sense of connection to a larger world. Long-duration isolation is known to produce anxiety, depression, irritability, and cognitive changes, even under relatively benign conditions. Studies of Antarctic researchers, submarine crews, and space station astronauts all point to the same conclusion. Isolation, confinement, and monotony strain the mind. Conflicts intensify. Small frustrations grow large. Motivation fluctuates. Now imagine living your entire life inside a metal structure, surrounded by the same few hundred people at most, with no possibility of leaving, no new environments to explore, no natural landscapes, no open sky. Imagine knowing, from birth, that you will never arrive, that the destination exists only for descendants you will never meet, that Earth is not just far away, but unreachable in any meaningful sense. This is not a temporary mission. It is existence. Human cultures are remarkably adaptable, but they rely on shared narratives, traditions, and expectations. A multi-century voyage would require a culture designed around deferred arrival, around duty to the future rather than fulfillment in the present. That is not impossible, but it is deeply unstable. Even on Earth, societies fracture over far smaller stresses. Then there is reproduction. For a journey lasting longer than a human lifespan, the crew must reproduce. Children must be conceived, carried, born, and raised in space. Pregnancy and development are exquisitely sensitive processes. Gravity, radiation exposure, nutrition, and stress all play critical roles. We do not yet know how human embryonic development proceeds in low or artificial gravity over the long term. We do not know how radiation exposure affects fetal development across generations. We do not know whether certain subtle effects would accumulate, compounding risks with each generation. Even small increases in mutation rates can have large consequences over time. Medical care presents another quiet problem. On Earth, Modern medicine depends on infrastructure, sterile environments, diagnostic equipment, pharmaceuticals produced in massive industrial systems, specialist knowledge distributed across millions of professionals. A spacecraft must carry all of this knowledge and much of this capability with it. Equipment must be repairable, supplies must last or be manufacturable on board, medications degrade over time, antibiotics lose potency, complex devices fail, and when something truly novel happens, a disease, a genetic condition, an unexpected complication, there is no hospital to transfer the patient to, no expert to consult in real time, no external rescue. The crew must solve every problem with what they have. This extends to injuries as well. A broken bone, a surgical emergency, a neurological event, all must be managed in an environment where mistakes cannot be undone and replacements cannot be delivered. Now consider sleep. Human sleep is governed by circadian rhythms tuned to Earth's rotation and light cycles. Disruptions to these rhythms affect cognition, mood, immune function, and metabolic health. Even with artificial lighting, maintaining a stable, healthy sleep cycle over decades in an enclosed environment is challenging. Chronic sleep disruption amplifies every other problem. It worsens mental health. It impairs immune function. It reduces lifespan. Then there is nutrition. A closed ecological system must recycle water, oxygen, and nutrients perfectly. Plants must grow reliably. Microbial systems must remain balanced. Contamination, crop failure, or ecological drift could have catastrophic consequences. On Earth, agriculture benefits from redundancy. If one crop fails, another can be planted. If a disease spreads, regions can be isolated. On a spacecraft, a single systemic failure could affect everyone at once. Food is not just calories. It is micronutrients. It is variety. It is culture. Monotonous diets affect morale and health over time. Even waste management becomes critical. Waste must be recycled efficiently, without introducing pathogens or toxic byproducts. This system must operate continuously for centuries without major failure. All of this assumes that the spacecraft itself remains intact. Materials degrade, metals fatigue, polymers break down, microfractures accumulate, temperature cycling, radiation exposure, and constant stress test every component. On Earth, we maintain infrastructure constantly. Bridges are inspected, buildings are repaired, machines are replaced. A spacecraft cannot be replaced. It must be self-maintaining indefinitely. And then there is the simple issue of accidents. Over centuries, the probability of something going wrong approaches certainty. A fire, a hull breach, a system failure, a cascade of small problems that align in the worst possible way. On Earth, disasters can be localized. In space, everything is connected. One failure can threaten the entire habitat. At this point, the question of travelling 1 light year has transformed completely. It is no longer about speed or distance. It is about whether a human body and a human society can be sustained in an artificial environment for longer than recorded human history, without external support while exposed to conditions that actively work against biological stability. Even if every technical problem could be solved, and many of them are not close to being solved, the burden placed on the human body remains extraordinary. This is why discussions of interstellar travel often drift toward concepts like suspended animation or cryogenic sleep. The idea is to bypass biology rather than support it continuously. Slow cellular processes, pause aging, reduce metabolic demands, but these ideas remain speculative. We do not know how to safely stop and restart a human body. We do not know how freezing or deeply suppressing biological activity affects the brain, memory, or identity. Damage that occurs silently during storage could be irreversible. And even if such techniques were perfected, they would introduce new risks. System failures during suspension, power loss, gradual degradation unnoticed until revival. The human body is not a machine that can be turned off and on without consequence. What becomes clear, slowly and unmistakably, is that a light year is not just a measure of distance through space. It is a measure of endurance far beyond what human biology evolved to handle. It stretches time beyond lifespan. It exposes bodies to radiation beyond safe limits. It demands isolation beyond psychological tolerance. It requires ecological and medical perfection beyond anything humanity has ever achieved for more than a few decades. This does not mean humans are weak. Quite the opposite. Our bodies are astonishingly adaptable within a certain range. We survive in deserts, polar regions, high altitudes and underwater habitats. We adjust to night shifts, long voyages, and extreme environments. But every adaptation has limits. A light year pushes past many of them at once. As this sinks in, another perspective begins to form. Perhaps the question is not why humans cannot travel even 1 light year, but why we expect that we should be able to. Our success on Earth and near-Earth space has trained us to believe that every boundary is temporary. Some boundaries are different. They are not walls built by ignorance or lack of effort. They are consequences of how matter, energy, and life interact. Understanding that does not diminish human ambition. It refines it. It suggests that our role in the universe may not be to physically cross every distance, but to understand them, to observe, to model, to send instruments where bodies cannot go, to extend perception rather than presence. Machines do not age. They do not suffer isolation. They do not require sleep or oxygen. They can travel slowly without despair. They can endure radiation better than flesh. Perhaps that is why, when we look outward, we increasingly do so through probes and telescopes rather than plans for crude starships. It's one thing to say that 1 light year is about 9.46 trillion kilometers. It's another thing entirely to feel what that means. Numbers of that size tend to slide off the mind. They sound impressive, but they don't anchor themselves to experience. They don't attach to anything we've lived through. So the distance remains distant in more ways than one. To make sense of it, the only option is to bring it down to human scale, not by shrinking the universe, but by stretching our everyday experiences until they finally snap. Let's start with something familiar: walking. An average human walks at about 5 kilometers per hour. At that pace, walking non-stop, without sleep, without stopping to eat, without slowing down, it would take roughly 200,000 hours to walk around Earth once. That's about 23 years. Obviously no one does this, but it gives us a baseline. Now imagine walking to the moon. At the same pace, it would take about 8.7 years. Already this feels absurd. You would need to start before you were born and finish long after you were gone. But let's keep going. Walking to the sun would take about 3,400 years. That alone is enough to signal that we've left ordinary experience behind. Civilizations have risen and fallen in less time than that walk would take. Languages would be born and forgotten. Borders would appear and vanish. The world would not be the same place by the time you arrived, assuming arrival even made sense. Now remember that 1 light year is about 63,000 times farther than the distance from Earth to the Sun. At walking speed, covering 1 light year would take more than 200 million years. Not 200 million days, not months, years. That is longer than mammals have existed on Earth. It is longer than the time since the first flowering plants appeared. You would begin your walk before the dinosaurs went extinct, and you still would not arrive today. Walking clearly doesn't work, but of course that's not how we travel long distances, so let's upgrade. Consider driving. At highway speed, say 100 kilometers per hour, you could circle Earth in about 400 hours, or a little over 2 weeks. That feels manageable. Driving to the moon would take about 160 days. Driving to the sun would take roughly 170 years. Already that last number is pushing past individual human lifetimes. Now apply the same multiplier. Driving 1 light year at 100 kilometers per hour would take about 10.8 million years. That's long enough for continents to shift noticeably, long enough for species to evolve into new forms, long enough that the stars themselves would not be in the same positions by the time you arrived. Even if you upgraded again, traded the car for a jet plane travelling at 900 kilometers per hour, you're still looking at over 1 million years to cross 1 light year. So let's go faster still. The fastest passenger aircraft ever built, the Concorde, cruised at about 2,180 kilometers per hour. At that speed, 1 light year would still take around 500,000 years, 500,000 years. This is not a subtle gap. This is not something that can be closed with incremental improvements. Doubling the speed does not halve the problem in any meaningful way when the baseline is already geological time. So perhaps we should stop thinking about human-scale vehicles altogether and look at spaceflight. The fastest spacecraft humans have ever built, as mentioned earlier, reaches speeds of roughly 700,000 kilometers per hour under optimal conditions. That sounds extraordinary because it is. At that speed, you could reach the moon in about 33 minutes. You could reach the sun in about 90 days. Those numbers sound impressive until you apply them to a light year. At 700,000 kilometers per hour, 1 light year takes about 1,500 years. Now, this is where intuition often falters. 1,500 years sounds smaller than millions. It feels closer. It feels like something that history could absorb. But think about what 1,500 years actually represents. 1,500 years ago, the Roman Empire was still standing. There were no telescopes, no electricity, no understanding of gravity beyond basic observation. Entire worldviews have risen and fallen in that span of time. A journey that takes 1,500 years is not a mission. It is a legacy project, a cultural artifact, something begun by one civilization and completed, perhaps, by another entirely. And that assumes constant maximum speed, no failures, no need to decelerate, and no need to adjust course. The everyday problem with 1 light year is that it refuses to stay connected to human timescales. No matter how you slice it, it breaks free. Let's try a different approach. Imagine stacking familiar distances end to end. If you stack the distance from New York to Los Angeles, about 4,000 kilometers, end to end, you would need to do that more than 2 billion times to reach 1 light year. If you stacked the circumference of Earth, about 40,000 kilometers, end to end, you would need about 236 million Earth circumferences to reach 1 light year. If you stacked the Earth-Moon distance, you would need nearly 25 million of them. If you stacked the Earth-Sun distance, you would need more than 63,000 of them. None of these stacks fit comfortably in the mind. They don't form a picture, they form a blur. So let's shift perspective again. Imagine time instead of distance. Suppose you left Earth today in a spacecraft travelling at the speed of our fastest probe. By the time you reach 1 light year away, if everything went perfectly, every nation on Earth would have experienced dozens of generations of change. The political map would be unrecognisable. Languages would have shifted. Some might have disappeared entirely. New ones would exist that we cannot imagine. The star you were heading toward would still be there, but Earth would not be the same Earth you left. This matters because travel is not just about arriving somewhere. It's about remaining connected to where you came from. Human journeys have meaning because they occur within shared time. You leave, you return, or at least you send messages that arrive within the same cultural context. 1 light year dissolves that context. Communication delays alone break it apart. A message sent from 1 light year away takes 1 year to arrive. A reply takes another year to come back. Conversations stretch into years. Coordination becomes impossible. Emotional continuity evaporates. Imagine sending a message saying, "We need help," and knowing that even if help were possible, the response would not arrive until 2 years later, and by then the situation might be completely different. Now imagine this at 4 light years, 8 years round trip, or 10, or 50. At some point, communication becomes history rather than dialogue. Another everyday comparison helps clarify the issue. Think of a calendar. Most people plan days or weeks ahead. Some plan months. A few plan years. Very few plan decades in detail. The further ahead you plan, the fuzzier everything becomes. Goals become vague. Assumptions pile up. Uncertainty dominates. A light year demands planning centuries ahead. Not just planning, but execution. Without interruption, without deviation, without collapse. That's not how human systems behave. Human infrastructure struggles to maintain continuity for decades. Even the most stable institutions change leadership, priorities, and structure over time. Maintenance lapses, records are lost, knowledge degrades or is reinterpreted. Now imagine a system that must operate flawlessly for centuries in isolation, while travelling through an environment that actively degrades materials and exposes everything to radiation. Everyday experience tells us that things wear out, machines fail, software becomes obsolete, replacement parts become unavailable, expertise is lost when people retire or pass away. A light year does not care. It demands that all of this be solved in advance. Let's try one more angle. Imagine shrinking the universe down so that the distance from Earth to the Sun is 1 meter. That's already a radical compression, but let's accept it. At that scale, Earth would be about the size of a grain of sand, and the Sun about the size of a large grapefruit. The Moon would be about 2.5 centimeters away. Now where would the nearest star be? About 270 kilometers away. That's like placing one grapefruit in your kitchen and another grapefruit in a different city. And that's just the nearest star. Most stars are much farther apart than that. This scale model is often used in astronomy education because it reveals something unintuitive. Space is not crowded, it is sparse. Stars are not packed together like lights on a ceiling. They are isolated points separated by enormous gaps. Travelling between them is not like moving between rooms. It is like moving between continents with no land in between. Everyday experience also tells us something else important. When distances become large enough, speed stops being the only issue. Reliability becomes the dominant concern. Driving across town, you don't worry much about breakdowns. Driving across a continent, you prepare more carefully. Driving across the entire planet without stopping would require extraordinary planning. Now extend that logic to a journey that lasts centuries. The probability of failure increases with time. Components fail, systems drift, unexpected interactions emerge. Even with redundancy, complexity introduces vulnerability. A light year magnifies this relentlessly. Every additional year of travel is another year where something can go wrong. And because you cannot turn back, cannot stop at a repair station, cannot call for immediate help, each failure compounds the risk. In everyday terms, 1 light year is the distance at which the idea of a trip stops making sense. It is the distance at which travel becomes something else entirely. Not a journey, but a process unfolding across generations. It's also the distance at which the word destination loses clarity. If no one who leaves will arrive, who is the traveller? If the people who arrive were not the ones who left, what does arrival mean? If the culture that launches the mission no longer exists when it completes, whose mission is it? These are not philosophical questions for their own sake. They are practical ones. They affect motivation, governance, responsibility, and meaning. Everyday human travel is anchored by personal experience. You go somewhere, you experience it, you return or you settle, you tell others. A light year strips that anchor away. This is why, when people hear 1 light year, it sounds small only until they try to connect it to anything they know. As soon as they do, the scale explodes outward. The distance is not just long. It is long in a way that breaks our usual categories. It is longer than projects, longer than plans, longer than lifetimes, longer than institutions. It pushes against the limits of what human continuity can sustain, and this is still just distance. We have not yet folded in the effects of speed on energy, on mass, on time itself. We have not yet confronted how motion at extreme velocities reshapes the problem rather than solving it. Once that enters the picture, the idea of casually crossing a light year becomes even less grounded in everyday reality. When people imagine travelling to the stars, speed is usually the first lever they reach for. If the distance is enormous, the solution feels obvious. Go faster, much faster, faster than anything before, faster than seems reasonable, faster than feels safe. Somewhere in that instinct sits a quiet belief that speed, if pushed far enough, will eventually overpower distance. To see why that belief runs into trouble, it helps to look carefully at the fastest things humans have ever actually built, not imagined, not proposed, built, launched, measured, and tracked as they moved through real space under real physical constraints. The list is shorter than you might expect. On Earth, the fastest human-made objects are not cars, planes, or even rockets in the way most people picture them. The fastest speeds we achieve here happen in very brief moments. Particles accelerated in laboratories can approach the speed of light, but they do so over microscopic distances and for fractions of a second. They are not vehicles. They do not carry structure, systems, or people. They are flashes of motion, not sustained journeys. For sustained, controlled travel through space, the record holders look much more modest. Start with aircraft. The fastest piloted airplane ever flown was the North American X-15, a rocket-powered experimental aircraft that reached a top speed of about 7,274 kilometers per hour in the late 1960s. That number still sounds impressive, and it is. At that speed, you could cross the continental United States in less than 25 minutes. But scale matters. At 7,274 kilometers per hour, travelling 1 light year would take roughly 1.5 million years. That's not a rounding error. That's a reminder that even the fastest aircraft ever built are irrelevant at interstellar scales. So we leave the atmosphere behind. Rockets are where things get serious. Chemical rockets remain the backbone of all human spaceflight. They are powerful, reliable, and brutally simple. Burn fuel, throw mass backward, move forward. The fastest crewed spacecraft ever flown was Apollo 10 during its return from the Moon. At its peak, it reached about 39,900 kilometers per hour relative to Earth. That record still stands. At that speed, 1 light year would take around 27,000 years. Not one lifetime, not a few generations, long enough for entire species to rise and disappear. Uncrewed spacecraft can go faster because they don't need to slow down as much and don't carry life support systems. The fastest spacecraft launched from Earth is a probe designed to study the Sun. By using gravity assists and diving deep into the Sun's gravitational well, it reached speeds of roughly 700,000 kilometers per hour relative to the Sun. That number finally feels different. 700,000 kilometers per hour is fast enough to circle Earth about 17 times in 1 hour. It's fast enough that the idea of speed becomes difficult to visualize. This is the point where many people intuitively think, okay, now we're getting somewhere. And in a sense, we are. At 700,000 kilometers per hour, 1 light year takes about 1,500 years. This is the absolute high watermark of human-built objects moving through space under sustained conditions. And even here, the distance remains overwhelming. 1,500 years is still far beyond any mission we know how to design. It's longer than recorded history in many parts of the world. It's longer than the lifespan of entire civilizations. And it's important to notice something else. That speed was achieved under very specific conditions. The spacecraft was not accelerating constantly. It used gravity to steal energy from the Sun. It followed a carefully calculated trajectory. It is not a vehicle you could point toward a star and simply keep going. Once it leaves the Sun's influence, it will slow relative to the Sun. It cannot maintain that peak speed indefinitely in interstellar space. This matters because speed records are often misunderstood. They are snapshots, not cruising velocities. When a spacecraft reaches a high speed near a planet or star, It does so because it is falling into a gravitational well. As it climbs back out, it gives that energy back. Net speed relative to the wider galaxy does not magically remain high unless additional propulsion is applied. So when we talk about the fastest things humans have built, we are really talking about brief moments of extreme motion, not sustainable interstellar travel. Now let's talk about propulsion itself, because this is where limits begin to assert themselves clearly. Chemical rockets are powerful, but they are inefficient in terms of energy per unit mass. Most of the rocket's mass at launch is fuel, and most of that fuel is used just to lift the rest of the fuel. By the time a spacecraft reaches space, it has already discarded the majority of its launch mass. This is not poor engineering. It's physics. The faster you want to go, the more fuel you need. The more fuel you need, the heavier you are. The heavier you are, the more fuel you need to move that mass. This feedback loop grows rapidly and becomes punishing at high speeds. Chemical rockets top out quickly because the energy stored in chemical bonds is limited. No amount of clever design changes that fundamental constraint. Other propulsion concepts aim higher. Ion engines, for example, are extremely efficient. They produce tiny amounts of thrust, but they can operate continuously for years. Over long periods, they can accelerate spacecraft to high speeds. This sounds promising until you look at the numbers. Ion engines produce thrust measured in fractions of a newton. They are wonderful for gentle, precise adjustments over long durations. They are not suited for accelerating large, massive spacecraft to extreme velocities. Using ion propulsion, you might eventually reach tens of kilometers per second. That's excellent by spaceflight standards. It is still negligible compared to the speed of light. Even nuclear propulsion, which taps into energies far beyond chemistry, faces limits. Nuclear thermal rockets could, in theory, double or triple the efficiency of chemical rockets. Nuclear electric propulsion could power more capable ion engines. These technologies could significantly reduce travel times within the solar system. They do not bring interstellar travel within reach. To cut a 1,500-year journey down to even 150 years, you would need to increase speed by an order of magnitude. To reach 15 years, another order of magnitude. Each step becomes exponentially harder. As you push toward higher fractions of light speed, something else happens. Energy requirements explode. The kinetic energy of an object increases with the square of its velocity. Double the speed, and the energy required quadruples. At relativistic speeds, the relationship becomes even more extreme. To accelerate a modestly sized spacecraft to just 10% of the speed of light would require energy comparable to the total annual energy output of human civilization directed into a single object. And that's only for acceleration. You still have to slow down. There is no free lunch in physics. Energy spent speeding up must be spent again slowing down, unless you're content to fly past your destination forever. So when we list the fastest things humans have ever built, we are not listing stepping stones toward the stars. We are mapping the edges of what our current understanding and resources allow. The fastest human-made objects are impressive because they reveal how hard it is to move through space at all. They also reveal a subtle truth. Speed alone does not solve distance. It magnifies other problems. At higher speeds, collisions become catastrophic. A grain of dust at a significant fraction of light speed carries kinetic energy equivalent to an explosive device. Shielding against such impact adds mass. Added mass demands more energy. More energy demands more fuel. At higher speeds, navigation becomes less forgiving. Tiny errors accumulate rapidly. Course corrections require enormous energy. A miscalculation early in the journey can send you missing your target by astronomical distances. At higher speeds, radiation exposure increases. High-energy particles become more dangerous. Cosmic rays strike with greater effect. Electronics degrade faster. Biological tissue suffers more damage. At higher speeds, time itself behaves differently. Time dilation becomes significant. From the perspective of the traveller, time passes more slowly. From the perspective of the rest of the universe, the traveller ages normally. This might sound helpful, but it introduces complications. Communication delays remain, coordination becomes difficult. The psychological effects of extreme relativistic travel are unknown. And all of this still assumes that the propulsion system can operate reliably for decades or centuries without failure. When people ask why humans cannot travel even 1 light year, the answer is not that we lack ambition or imagination. It's that the fastest things we have ever built already sit near the edge of what physics allows using technologies we understand. We are not crawling. We are sprinting as fast as we can, and the finish line is still unimaginably far away. There's also a quiet mismatch between how speed feels and how it works in space. On Earth, increasing speed often feels linear. A faster car gets you there sooner. A faster plane shortens the trip. Improvements stack up in intuitive ways. In space, speed becomes slippery. Gains come at enormous cost. Improvements produce diminishing returns. Every additional increment of velocity requires disproportionate effort. This is why so many proposed interstellar concepts rely on external energy sources. Light sails pushed by powerful lasers, magnetic sails interacting with interstellar plasma, concepts that attempt to avoid carrying fuel altogether. Even these ideas face immense challenges. The infrastructure required to power them is vast. The precision required is extreme. The margins for error are tiny. And most importantly, none of them have been built at the scale required. They remain ideas, not records. What we know for certain is this: the fastest things humans have ever built can cross the solar system. They can escape the sun's gravity. They can wander into interstellar space carrying messages about where they came from. They cannot cross a light year in anything resembling a human timescale. This is not because engineers are unimaginative. It is because physics sets the rules of the game, and speed is one of the most expensive moves you can make. As this becomes clearer, another realization begins to form. Perhaps speed is not the main obstacle at all. Perhaps it's simply the most obvious one. At some point, speed stops feeling like a solution and starts behaving like a problem. Not suddenly, not dramatically. It happens quietly, the way a helpful tailwind turns into turbulence as conditions change. At low velocities, speed is friendly. It shortens trips. It increases efficiency. It makes travel feel powerful and controlled. But as you push farther and farther beyond familiar ranges, speed begins to demand payment in places you didn't expect. Long before a spacecraft reaches its destination, speed itself becomes the obstacle. The first reason is deceptively simple. Energy does not scale kindly. To move faster, you must add energy. That seems obvious. What's less obvious is how aggressively the cost rises. In everyday life, doubling speed might mean doubling fuel consumption or power output. In space, especially at extreme velocities, doubling speed can require many times more energy than before. This is not a matter of poor engineering or inefficiency. It is a consequence of how motion works. At relatively low speeds, the kinetic energy of an object increases with the square of its velocity. That means if you double your speed, you quadruple the energy required, triple your speed, and you need 9 times the energy. This alone becomes punishing very quickly, and this is still before relativity fully enters the picture. As speeds climb higher, approaching a significant fraction of the speed of light, the relationship grows even harsher. Relativistic effects come into play. From the perspective of an external observer, the object becomes harder to accelerate. Not because its rest mass increases in a literal sense, but because energy and momentum behave differently at those scales. Each additional increment of speed costs more energy than the last. This means that speed improvements suffer from diminishing returns. You spend enormous effort to gain a little more velocity, and each new gain is harder than the previous one. The universe does not reward persistence here. It penalizes it. Then there is fuel, which turns speed into a logistical nightmare. Most propulsion systems work by expelling reaction mass. You throw something backward to move forward. The faster you want to go, the more reaction mass you must throw, and the faster you must throw it. Carrying fuel adds mass. Mass makes acceleration harder. Harder acceleration requires more fuel. This feedback loop is merciless. Even advanced propulsion concepts cannot escape it entirely. Some reduce the amount of reaction mass required. Others improve efficiency, but none remove the fundamental link between speed, energy, and mass. At high velocities, fuel is not just heavy, it becomes the dominant design constraint. The spacecraft begins to look less like a vehicle and more like a tank of propellant with a small payload attached. This creates a paradox. To reach the speeds needed to make interstellar travel feasible, you must carry enormous amounts of fuel. But carrying that fuel makes it harder to reach those speeds. Speed becomes self-defeating. Now add deceleration. Getting up to speed is only half the problem. Arriving anywhere useful requires slowing down. You cannot simply streak through a star system at a significant fraction of light speed and expect to stop casually. Braking requires energy or interaction with something external, or both. If you use fuel to decelerate, you need just as much fuel as you use to accelerate. Often more, because systems are less efficient when slowing down under load. This effectively doubles the energy requirement for the journey. If you try to use external methods, like magnetic braking against interstellar plasma or stellar winds, the forces involved are weak and unpredictable. They require large structures, long times, and precise conditions. They do not offer guaranteed control. Without reliable braking, speed turns into overshoot. You arrive too fast to stop, too fast to maneuver, too fast to do anything except pass through and continue onward. Speed, in this context, is not progress. It is momentum without purpose. Another issue emerges once you consider collisions. Space is not empty. It is sparse, but sparsity does not mean safety. Interstellar space contains dust grains, atoms, and occasional larger particles. At everyday speeds, these are negligible. At extreme velocities, they become deadly. Kinetic energy depends on velocity squared. That means a tiny particle, weighing almost nothing, can carry enormous energy if it strikes at high speed. A grain of dust impacting a spacecraft at a significant fraction of light speed would release energy comparable to an explosive weapon. Shielding against this is not straightforward. You can add physical armor, but that increases mass. Increased mass increases energy requirements. Increased energy requirements demand more fuel. More fuel increases mass again. You can add active shielding concepts like electromagnetic fields to deflect charged particles. But many interstellar particles are neutral. They do not respond to magnetic fields. They go straight through. At lower speeds, micrometeoroids are a manageable risk. At high speeds, they are a persistent, unavoidable hazard. Over decades or centuries, even a low probability of impact becomes a near certainty. Speed turns empty space into a shooting gallery. Radiation adds another layer. As speed increases, exposure to radiation changes. High-energy particles encountered head-on strike with greater relative energy. Shielding becomes less effective per unit mass. Electronics degrade faster. Biological tissue suffers greater damage. This is not merely cumulative exposure over time, it is intensified exposure per unit distance travelled. Speed amplifies the effect. Then there is navigation. At high velocities, small errors become large mistakes very quickly. A tiny deviation early in the journey compounds over time, leading to enormous positional errors at interstellar distances. Correcting these errors requires thrust. Thrust requires fuel. Fuel adds mass. Course correction windows shrink as speed increases. Reaction times shorten. Precision requirements tighten. At relativistic speeds, even detecting obstacles or adjusting trajectory becomes difficult. Sensors must operate faster. Control systems must respond with extreme reliability. Failures that might be recoverable at low speeds become catastrophic at high ones. Speed removes margin. Time itself enters the discussion here, but not in the comforting way people often imagine. Time dilation is frequently presented as a benefit of high-speed travel. If you travel fast enough, time passes more slowly for you. You could cross vast distances while aging less. This is true in a narrow mathematical sense. But it does not eliminate the problem. It shifts it. From the perspective of those who remain behind, the journey still takes the full amount of time. Communication delays remain. Support remains impossible. Coordination with any external system breaks down. From the perspective of the traveller, subjective time passes more slowly, but biology does not become invincible. Radiation damage still accumulates. Systems still degrade. Psychological effects still unfold, just compressed into a shorter personal timeline. Time dilation also complicates mission planning. The crew experiences events at a different temporal rate than the rest of civilization. Decision-making becomes asynchronous. Any hope of shared context evaporates. Speed stretches not just time, but relationships. There is also the issue of heat. High-speed travel through space generates heat through particle impacts and system operation. Managing heat in space is already challenging because there is no air to carry it away. Heat must be radiated. Radiators add mass and surface area. Surface area increases exposure to radiation and impacts. At higher speeds, thermal management becomes increasingly difficult. Systems must dissipate more energy while remaining protected. Failures cascade quickly. Speed creates stress in places you cannot easily reinforce. And then there is reliability. A journey at extreme speed must be sustained for long durations. Engines must operate flawlessly. Control systems must never glitch. Power systems must remain stable. Software must handle edge cases no one has encountered before. On Earth, high-speed systems benefit from constant maintenance. Planes are inspected regularly. Cars are serviced. Even experimental systems are supported by entire teams. A spacecraft traveling at extreme speed through interstellar space has none of that. It must be self-sufficient, self-repairing, self-correcting. The faster it goes, the less forgiving failure becomes. At some point, speed stops reducing travel time in a meaningful way and starts increasing risk faster than it reduces duration. This is the point where speed becomes an enemy. It demands more energy than we can reasonably supply. It amplifies hazards that were once negligible. It removes safety margins. It magnifies the consequences of small errors. Distance does not yield politely to velocity. It pushes back. This is why so many serious discussions of interstellar travel eventually slow down rather than speed up. They focus on endurance rather than sprinting, on probes rather than cruise, on patience rather than haste. It is also why the fastest things humans have ever built do not represent a path forward so much as a warning sign. They show how quickly benefits flatten out and costs explode. The intuitive idea that going faster solves the distance problem works only up to a point. Beyond that point, speed reshapes the problem into something more complex, more dangerous, and less human. Fuel sounds like a practical concern, mundane even. Something you calculate, load, and mostly forget once the engines ignite. On Earth, fuel is inconvenient but familiar. You fill a tank, drive somewhere, refill it again. In spaceflight, fuel is something else entirely. It becomes a governing force, a quiet dictator shaping every decision long before anything ever launches. This is where the rocket equation enters the story, and with it, the realization that fuel is not just a resource. It is a constraint so strict that it borders on tyrannical. The rocket equation is not a design choice. It is not a guideline. It is a law. It describes the relationship between how fast a spacecraft can change its velocity, how efficient its engines are, and how much mass it carries as fuel, and it does so without sympathy for ambition. At its core, the equation says something deceptively simple. To go faster, you must expel mass. The faster you want to go, the more mass you must expel. And the more mass you carry to expel later, the more mass you must expel now to carry it. This creates a spiral that tightens quickly. Imagine a rocket sitting on the launch pad. Most of what you see is fuel, not cargo, not instruments, not people, fuel. As the rocket ascends, it burns fuel just to lift the remaining fuel. Stage by stage, empty tanks are discarded to shed mass, because keeping them would make further acceleration inefficient or impossible. This process works well enough to reach orbit. Barely. Reaching orbit around Earth requires a change in velocity of about 9.4 kilometers per second. That number already pushes chemical rockets close to their practical limits. Most of the rocket's initial mass is fuel. Only a tiny fraction ends up in orbit as payload. Now consider what happens when you ask for more velocity. If you want to double the change in velocity, you do not need double the fuel. You need exponentially more. The exact amount depends on engine efficiency, but the pattern is relentless. Each additional increment of speed costs more fuel than the last. This is why rockets look the way they do. Tall, narrow, mostly tank, and this is why interstellar travel collapses under the weight of fuel requirements long before any other problem has a chance to dominate. Let's put some numbers on this, not to overwhelm, but to ground the idea. A typical chemical rocket engine has an exhaust velocity of around 4.5 kilometers per second. That number represents how fast the expelled fuel leaves the engine. It sets the efficiency ceiling for that engine type. The rocket equation relates exhaust velocity to how much your spacecraft's speed can change based on how much mass you're willing to lose as fuel. If you want a change in velocity equal to your exhaust velocity, you need to burn about 63% of your initial mass as fuel. If you want twice that velocity change, the fuel fraction climbs sharply, 3 times, steeper still. By the time you reach velocity changes relevant to interstellar travel, the fuel fraction approaches absurdity. The payload becomes vanishingly small compared to the fuel required to move it. And this assumes you only accelerate once. You must also slow down. Acceleration without deceleration is not travel, it is escape. If you accelerate halfway to your destination and then decelerate the rest of the way, the fuel requirements effectively square. You need fuel to carry fuel that will later be used to slow down. This is where the rocket equation becomes suffocating. For chemical rockets, the numbers quickly exceed anything that could be launched from Earth, assembled in space, or sourced from reasonable amounts of material. You would need fuel masses larger than cities, larger than mountains, larger than small asteroids. Even if you somehow gathered that much material, accelerating it would require engines beyond what chemistry can provide. So naturally people look beyond chemical rockets. Nuclear propulsion is often suggested as the next step. Nuclear reactions release far more energy per unit mass than chemical reactions. That's true. But the rocket equation does not go away. It merely loosens its grip slightly. Nuclear thermal rockets, which heat a propellant using a nuclear reactor, could roughly double exhaust velocity compared to chemical engines. That's a meaningful improvement for travel within the solar system. It is not transformative for interstellar distances. Doubling exhaust velocity does not halve fuel requirements. It shifts the curve, but the curve remains exponential. You still face fuel ratios that balloon beyond practicality as velocity demands increase. Nuclear electric propulsion, where nuclear reactors power ion engines, offers higher efficiency but extremely low thrust. These systems can operate for years, gradually increasing speed. They're excellent for deep space probes. They're unsuitable for accelerating massive spacecraft to extreme velocities. The tyranny of fuel is not just about energy density. It is about carrying your past decisions with you. Every kilogram of fuel you load must be accelerated. Every kilogram of fuel used early must have been carried by fuel burned even earlier. The past never lets go. This becomes even more severe when you include life support systems. Humans require air, water, food, shielding, living space, medical equipment, and redundancy. All of this adds mass. That mass must be accelerated. Accelerating it requires fuel. Carrying that fuel requires more fuel. The rocket equation does not care whether the mass is useful or not. It treats everything equally. Even clever strategies like staging, where you drop empty tanks to reduce mass, only work within certain bounds. They help rockets escape Earth's gravity. They do not scale cleanly to interstellar missions that must carry everything from start to finish. Some concepts attempt to escape the tyranny by not carrying fuel at all. Light sails, for example, use radiation pressure from light to push a spacecraft. If you shine a powerful laser at a reflective sail, the photons transfer momentum, accelerating the craft without onboard fuel. This neatly sidesteps the rocket equation. But it introduces new problems. The lasers required would need to be unimaginably powerful and precisely aimed over astronomical distances. The sail would need to be enormous, thin, and perfectly controlled. Even small deviations could tear it apart or send it off course. And braking remains unsolved. You can accelerate with a laser, but slowing down at the destination requires either another laser waiting there, which implies prior infrastructure, or interaction with interstellar media that may be too weak to matter. Magnetic sails and electric sails attempt similar tricks, interacting with solar wind or interstellar plasma. These forces are extremely faint. They require vast structures and long times to have any effect. Again, the rocket equation may loosen its grip, but distance and time step in to take its place. Antimatter propulsion is sometimes invoked as the ultimate solution. Matter-antimatter annihilation releases enormous amounts of energy. In theory, it offers unmatched energy density. In practice, antimatter is extraordinarily difficult to produce, store, and control. We can create tiny amounts in particle accelerators at tremendous cost. Storing it safely requires complex magnetic traps. Any contact with ordinary matter results in immediate annihilation. Even if antimatter engines were perfected, the rocket equation would still apply. You still need reaction mass unless you rely entirely on photon propulsion, which introduces inefficiencies and control challenges. And then there is heat. Managing the waste heat from such reactions would be a serious problem. Radiators would need to be enormous. Radiators add mass. Mass demands fuel. The loop never breaks. Fuel tyranny also extends to reliability. Engines that operate for long durations must be robust. Fuel systems must remain stable. Storage must not degrade. Leakage, contamination, or chemical breakdown can doom a mission years or centuries before arrival. On Earth, fuel systems are monitored constantly. Components are replaced. Maintenance is routine. In interstellar space, everything must work indefinitely or fail gracefully without external support. This places extreme demands on material science, manufacturing, and system design. Every valve, every pump, every seal must perform perfectly across timescales longer than any machine in history has ever been expected to endure. At some point, the question shifts. It stops being, how do we carry enough fuel, and becomes, why are we trying to carry fuel at all? That question is not rhetorical. It reflects a growing recognition that interstellar travel, if it ever happens, may require fundamentally different approaches. Not better rockets, but different strategies. Perhaps energy is gathered along the way. Perhaps acceleration happens slowly over decades using external forces. Perhaps only the smallest payloads are sent, stripped of everything unnecessary. Perhaps humans are not the payload. Because when you look honestly at the rocket equation, it becomes clear that fuel does not scale with dreams. It scales with mass and velocity, and those do not negotiate. Every attempt to push against this law increases complexity, cost, and risk. The equation does not forbid interstellar travel outright. It simply demands payment in a currency we do not possess in sufficient quantities. Understanding this reframes the problem. It is not that we lack imagination. Engineers have imagined countless propulsion concepts. It is not that we lack courage. Humanity has shown a willingness to attempt the improbable many times before. It is that the universe enforces its bookkeeping strictly. Every joule must be accounted for, every kilogram must be paid for in energy, every second of acceleration carries consequences that cannot be wished away. The tyranny of fuel is not dramatic. It is quiet, mathematical, and absolute. It does not shout. It simply sits there, waiting for the numbers to be written down and then refuses to bend. At first, the idea sounds manageable. Bring what you need, plan carefully, pack efficiently. Humans have been doing this for as long as we've travelled. Expeditions crossed oceans with limited supplies. Space missions carry everything their crews require for months at a time. So when the question of interstellar travel comes up, it feels reasonable to assume the same logic applies, just on a larger scale. That assumption breaks down quietly, then completely. Because carrying everything with you for a journey measured in years is one thing. Carrying everything with you for a journey measured in centuries is something else entirely. At that point, the problem is no longer logistics, it is survival under permanent isolation. Start with the most basic requirement: air. A human breathes roughly 11,000 litres of air per day. Oxygen itself can be recycled, but recycling systems are not perfect. Carbon dioxide must be removed. Trace contaminants accumulate. Filters clog. Chemical scrubbers degrade. Biological systems drift out of balance. On the International Space Station, air recycling works because parts can be replaced, systems can be serviced, and problems can be corrected with help from Earth. On an interstellar journey, there is no Earth. Every component must work not just reliably, but indefinitely. Any gradual degradation becomes a long-term threat. A small inefficiency that is tolerable over months becomes fatal over decades. A flaw that takes years to show itself may not be discovered until it is too late to correct. Then there is water. Water is heavy. 1 litre weighs 1 kilogram. Humans need several litres per day for drinking alone, not counting hygiene, food preparation or medical use. Like air, water can be recycled, and modern systems are quite efficient. But again, efficiency is not perfection. Losses accumulate, leaks happen, contamination occurs. Microorganisms grow in unexpected places. Pipes corrode, valves fail. On Earth, water infrastructure is vast and redundant. On a spacecraft, it is compact, closed, and fragile by comparison. Every kilogram lost must be accounted for because there is no resupply. Food introduces even more complexity. Humans do not just need calories. They need a balanced intake of proteins, fats, carbohydrates, vitamins, and minerals. They need variety to avoid deficiencies and maintain morale. They need food that remains safe and nutritious over long periods. Stored food degrades. Vitamins break down. Fats oxidize. Packaging fails. Even freeze-dried food has a shelf life measured in years, not centuries. This is why serious long-duration mission concepts rely on growing food. But growing food means carrying soil or nutrient solutions, seeds, lighting systems, temperature control, pollination mechanisms, and waste recycling systems. It means managing ecosystems. Ecosystems are not static. They evolve, they fluctuate, they develop imbalances. On Earth, ecosystems recover because they are vast, interconnected, and resilient. On a spacecraft, the ecosystem is small, isolated, and vulnerable. A plant disease, a microbial bloom, or a pest infestation could spread unchecked. A crop failure could cascade into malnutrition. Nutrient cycling could drift slowly until something breaks. Food production also requires energy. Lighting alone for plant growth consumes enormous power. That power must be generated continuously. Power systems must be redundant. Redundancy adds mass. Mass adds fuel requirements. Fuel compounds the problem again. Medical care expands the list further. Humans get sick, they are injured, they develop chronic conditions. Over a long enough timeline, statistically everything that can happen will happen. Medical care requires equipment, pharmaceuticals, diagnostic tools and trained personnel. Medications have expiration dates. Some require refrigeration, others degrade in radiation. Surgical tools must remain sterile. Imaging equipment must remain calibrated. On Earth, medicine works because it is supported by a massive supply chain and a constantly updated body of knowledge. New treatments emerge, old ones are replaced, specialists consult each other. On an interstellar spacecraft, medical knowledge is frozen at launch unless systems for research, experimentation, and education are built in. Even then, the ability to respond to unknown conditions is limited. What happens when a crew encounters a disease that does not exist at launch, or a genetic condition that emerges over generations, or psychological disorders exacerbated by isolation? There is no hospital to transfer patients to, no pharmaceutical manufacturer to call, no emergency evacuation. Now consider waste. Every system that consumes produces waste. Solid waste, liquid waste, biological waste, chemical waste. All of it must be processed, recycled, or stored safely. Poor waste management leads to contamination, disease, and system failure. Waste recycling systems must operate continuously and flawlessly. Microbial systems must remain stable. Byproducts must not accumulate to toxic levels. All of this must be monitored, controlled, and repaired if necessary. This is not trivial even on Earth. It becomes critical in a sealed environment. Then there is clothing, tools, spare parts. Materials wear out, fabrics tear, metals fatigue, plastics become brittle under radiation, lubricants degrade, electronics suffer bit errors, sensors drift. On Earth, broken items are replaced. In space, they must be repaired or remade. That means carrying manufacturing capabilities, 3D printers, raw materials, precision tools, testing equipment, skilled operators, quality control systems. Manufacturing in space is possible in principle. In practice, it adds enormous complexity. Each new capability requires support systems, training, maintenance, and energy. And every kilogram of manufacturing equipment adds to the mass that must be accelerated. The list continues. Living space must be sufficient to avoid psychological harm. Crowding increases stress, conflict, and mental illness. Spacious habitats require structure. Structure requires mass. Mass requires fuel. Radiation shielding must be thick enough to protect occupants. Shielding is heavy. Using water or fuel as shielding helps, but once those resources are consumed, protection diminishes. Artificial gravity systems, if used, require rotation. Rotation introduces mechanical stress. Bearings wear. Structures flex. Vibration propagates. Communication systems must function over decades or centuries. Antennas must remain aligned. Electronics must resist radiation damage. Software must remain compatible with evolving needs. Governance systems must manage conflict, decision-making, and succession. Social breakdown is not a technical failure, but it can destroy a mission just as effectively. Education systems must train new generations born aboard the spacecraft. Knowledge must be preserved and transmitted accurately. Cultural drift must be managed. None of this is impossible in isolation. What makes it overwhelming is that all of it must work together, continuously, without external support, for longer than any human-made system has ever operated. And all of it must be carried from the start. This is the core of the problem. Every solution to one issue creates additional mass. Every kilogram of mass amplifies every other problem. Fuel requirements rise, structural demands increase. Energy generation becomes harder. Failure modes multiply. There is no way to selectively carry only the easy parts. On Earth, specialization is possible because systems are distributed. Agriculture happens in one place, manufacturing in another, medicine somewhere else, energy production elsewhere still. If one region fails, others compensate. On a spacecraft, everything is local. Failure is not regional, it is global. This is why concepts like generation ships, massive self-contained habitats travelling between stars, remain theoretical. Not because they violate physics outright, but because they demand perfection across too many domains simultaneously. Human history offers a sobering comparison. Even large, stable societies struggle to maintain complex infrastructure over centuries. Roads decay, institutions reform or collapse, knowledge is lost and rediscovered, environmental conditions change, and those societies exist on a planet with abundant resources, natural ecosystems and external trade. A spacecraft has none of that slack. Even small mistakes echo for generations. Another subtle issue emerges when you carry everything with you. Flexibility disappears. On Earth, humans adapt by changing behaviour, technology, and environment. If one approach fails, another can be tried. If a resource becomes scarce, alternatives are found. On an interstellar journey, alternatives must already be on board. There is no improvisation beyond what was planned. No unexpected discovery of a new resource. No chance encounter that changes the equation. You live inside the consequences of decisions made long before you were born. This affects motivation and morale. It affects trust in leadership. It affects whether people feel agency over their lives or merely custodians of a mission they did not choose. The psychological burden of carrying everything with you is not just about confinement. It is about inevitability. Every object aboard the spacecraft matters. Every system has a history. Every resource has a finite limit. Waste is not something you discard. It is something you must live with. The environment becomes a closed loop, not just physically, but emotionally. And this loops back to mass again. If you want redundancy, you add mass. If you want safety margins, you add mass. If you want comfort, you add mass. If you want resilience, you add mass. Each addition feels reasonable in isolation. Together, they become crushing. This is why interstellar concepts often shrink the payload dramatically. Probes instead of people. Instruments instead of habitats. Data instead of lives. Machines do not need air. They do not eat. They do not reproduce. They do not suffer isolation. They can be turned off and on. They tolerate radiation better. They can be simpler. Even then, carrying everything with you remains a challenge. But it becomes manageable. For humans, it does not. This is not a failure of imagination. It's a reflection of how dependent human life is on a web of support that evolved on a planet, not in a vacuum. The more honestly you account for what humans require, the heavier the spacecraft becomes, not just physically but conceptually. It turns into a floating world that must be perfect forever, and perfection is not something engineering is good at. This realization doesn't arrive all at once. It settles gradually. It becomes clear not through dramatic impossibility, but through accumulation. A system here, a backup there, another contingency added, another layer of redundancy. Until finally, the question shifts again. Not, how do we carry everything with us, but what if we didn't? What if the assumption itself is wrong? That thought opens the door to radically different approaches. Not travelling as bodies, but as information. Not carrying ecosystems, but building them later. Not moving lives, but sending precursors. Before any of that can be evaluated, though, another constraint demands attention. One that does not care how carefully you pack or how lightly you travel. Time itself. At first, time dilation sounds like a gift, a loophole, a quiet concession from the universe, as if physics itself is offering a compromise. You can't cross vast distances quickly, it seems to say, but if you go fast enough, time will slow down for you. The journey will feel shorter. Your body will age less. The stars will drift past while you remain almost unchanged. It's an idea that feels reassuring, especially when the distances involved are so unforgiving. If 1 light year takes centuries at realistic speeds, Perhaps time dilation can shrink that burden into something human again. Perhaps you can trade velocity for longevity and slip through the problem sideways. But when you look closer, that comfort begins to fade. Time dilation is real. It has been measured repeatedly. Atomic clocks flown on airplanes tick more slowly than those on the ground. Satellites must correct for relativistic effects to keep GPS accurate. Astronauts age very slightly less than people on Earth because of their motion and altitude, so the effect itself is not speculative. What is often misunderstood is what time dilation actually solves and what it does not. Time dilation does not reduce the distance travelled. It does not reduce the energy required. It does not reduce exposure to hazards per unit distance. It does not eliminate the need for fuel, shielding, life support, or reliability. It changes the relationship between time experienced by the traveller and time experienced by everyone else. That distinction matters more than it first appears. Imagine a spacecraft travelling at a significant fraction of the speed of light. From the perspective of people on Earth, the journey takes centuries. From the perspective of the crew, due to time dilation, perhaps only decades pass. That sounds like progress. But notice what has not changed. The spacecraft still travels the same distance through space. It still encounters the same number of particles, the same radiation environment, the same collision risks. It still requires the same acceleration and deceleration. The engineering challenges remain unchanged. The only thing that changes is how much the crew ages during the trip. That helps with one problem, biological lifespan, but it introduces others. Start with communication. No matter how fast a spacecraft travels, signals sent back to Earth still move at the speed of light. If you're 1 light year away, your message takes 1 year to arrive. A reply takes another year to come back. This delay exists regardless of time dilation aboard the ship. From the crew's perspective, this is disorienting. They may experience only months or years between sending a message and receiving a response, but the content of that response reflects a world that has moved far ahead. People they knew may be gone. Institutions may have changed. Priorities may no longer align. Decisions made on Earth are based on outdated information from the ship. Decisions made on the ship are based on outdated information from Earth. Coordination breaks down. This is not a minor inconvenience. For any complex mission involving humans, coordination is safety. It is redundancy. It is the ability to adapt when something unexpected happens. Time dilation stretches the thread connecting the crew to the rest of humanity until it becomes thin and brittle. Then there is the psychological effect of temporal isolation. Human identity is deeply tied to shared time. We mark birthdays together. We experience news cycles together. We feel connected because events unfold at roughly the same pace for everyone around us. Relativistic travel fractures that shared pace. The crew begins to live in a different temporal world. Their experience of time diverges from everyone else's. They watch messages arrive from a future that feels distant and unfamiliar. They know that while they have aged a few years, decades may have passed back home. This creates a strange emotional displacement. The crew becomes unmoored from their origin culture. Not gradually, but structurally. Even if they remain in contact, the cadence of life no longer matches. Their reference points diverge. Their sense of belonging erodes. This is not something humans have experience managing. Even smaller temporal dislocations cause stress. People returning from long deployments often report feeling out of sync with society. Friends have changed, norms have shifted, shared experiences are missing. Now amplify that effect by decades or centuries. Time dilation also complicates governance and responsibility. Who is accountable for decisions made aboard the ship? The people who launched the mission? They may be long gone. The people receiving updates on Earth? Their responses arrive too late to matter in real time. Authority becomes ambiguous. The crew must be autonomous. That autonomy is necessary, but it also isolates them. There is no higher court to appeal to. no oversight that can intervene quickly, no shared legal or ethical framework evolving in parallel. This autonomy is not empowerment, it is burden. Another subtle issue arises when you consider health and biology more carefully. Time dilation reduces the rate at which biological processes unfold relative to Earth. That means aging slows from the crew's perspective, but damage does not necessarily scale the same way. Radiation exposure is measured per unit distance travelled, not per unit time experienced. At high speeds, especially relativistic speeds, exposure per unit distance can increase due to higher relative energies of incoming particles. From the crew's perspective, this means that radiation damage may accumulate faster relative to their subjective time. In other words, even though they age more slowly, they may experience higher radiation doses per year of lived experience. That is not a favourable trade. Cellular repair mechanisms operate at biological rates. DNA damage accumulates when repair cannot keep up. If damage per unit experience time increases, time dilation becomes a liability rather than a benefit. This effect is still an area of active research, but it highlights a crucial point. Time dilation does not create a protective bubble around biology. It simply alters clocks. There is also the issue of system longevity. From the crew's perspective, systems operate for a shorter subjective duration. From Earth's perspective, those same systems must function for centuries. Which perspective matters for engineering? Both. Mechanical components were based on cycles and stresses, not on how much time the crew feels has passed. Electronics degrade due to radiation exposure, thermal cycling, and material aging. Software must remain functional across hardware generations. A component that must survive 200 years must be designed differently from one that must survive 20. Time dilation does not reduce that requirement. It only reduces how long the crew waits for it to fail. If anything, this creates a mismatch. The crew experiences a shorter journey, but depends on systems that must endure far longer than their subjective experience suggests. Maintenance becomes psychologically harder. When a system failure is framed as something that occurred early in the journey from the crew's perspective, but decades in from Earth's perspective, planning becomes dissonant. Expectations drift. Risk assessments misalign. Then there is the problem of arrival. Time dilation does not change the fact that when the crew reaches their destination, the universe they left behind is far in the past. The culture, technology, and context that motivated the mission may no longer exist. This raises a question that is easy to overlook. Who is the mission for? If the crew arrives at a star system decades or centuries in Earth time after launch, what are they arriving to? Is there support waiting? Is there infrastructure? Is there even interest? Time dilation does not guarantee relevance. The mission risks becoming an artifact of a bygone era, arriving in a future that no longer shares its assumptions. There is also a practical navigation concern. At relativistic speeds, observing the universe changes. Light from ahead is blue shifted. Light from behind is red shifted. The sky compresses into a forward-facing cone. Visual cues distort. Navigation systems must account for these effects. Sensors must be calibrated for altered spectra. Data processing becomes more complex. Errors become harder to interpret. This adds cognitive load and technical risk. Time dilation also interacts with acceleration and deceleration phases, which are often glossed over in simplified explanations. Time dilation effects are strongest at high constant velocities. Getting to those velocities requires long periods of acceleration. If acceleration is limited to keep forces tolerable for humans, reaching relativistic speeds takes time. From Earth's perspective, a long time. From the crew's perspective, still a significant duration. During acceleration and deceleration, time dilation changes continuously. The crew experiences varying rates of time relative to Earth. Clocks must be synchronized carefully. Planning becomes complicated. And remember, All of this assumes propulsion systems capable of sustaining relativistic travel. That is already a speculative leap. When time dilation is presented as a solution, it often comes wrapped in an unspoken assumption that the crew's experience is all that matters. But human travel has never worked that way. Exploration is meaningful because it connects places and people, because knowledge flows back, because the traveller and the society remain in dialogue. Time dilation severs that dialogue. It creates a bubble in which the crew exists out of sync with everyone else. That bubble might preserve bodies, but it isolates lives. There is also the ethical dimension. If a crew embarks on a relativistic journey, knowing that they will return, if at all, to a world centuries removed from the one they left, what consent means changes? What obligation means changes? What success means changes? The mission becomes a one-way commitment not just in space, but in time. Even if the crew accepts this, future generations did not choose it. Children born aboard such a ship inherit a destiny shaped by relativistic physics. Their subjective time may pass quickly, but their separation from Earth is absolute. Time dilation does not soften that reality, it sharpens it. And then there is the quietest problem of all, meaning. Human lives are structured by time. We plan, we remember, we anticipate, we measure progress. Time dilation disrupts those structures. Milestones lose context, achievements lose comparison. The shared timeline that gives events significance fractures. This is not something engineering can fix. It is tempting to imagine that time dilation turns interstellar travel into a personal shortcut. That you leave, travel fast and arrive having skipped the waiting. But the universe keeps its accounts carefully. You may skip waiting, but you cannot skip consequences. The distance still exists. The energy still must be paid. The hazard still must be faced. The separation still unfolds. Time dilation does not reduce the difficulty of the journey. It redistributes it. It makes the journey easier for the traveller in one narrow sense, while making it harder for everyone else to remain connected to it. Once this is understood, time dilation stops looking like a solution and starts looking like a trade-off. One that solves a problem humans are comfortable naming, aging, by creating problems humans are less comfortable confronting, isolation, irrelevance, and disconnection. Out there, between the stars, nothing dramatic announces itself at first. No roaring storms, no glowing walls of danger. Interstellar space looks calm, almost empty, especially when compared to the violent imagery we associate with supernovae or black holes. That apparent calm is misleading. The dangers that make interstellar travel so difficult are not loud. They are quiet, persistent, and relentless, and they become more severe the farther and faster you go. Radiation is the first of these quiet hazards, and it is not a single thing. It is a category that includes several different sources, each with its own behaviour and risks. Near Earth, most of this radiation is deflected or absorbed before it can do much harm. The planet's magnetic field bends charged particles away. The atmosphere absorbs high-energy photons. Even when radiation does reach the surface, it is diluted enough that life has adapted to it over billions of years. Once you leave that protective cocoon, the balance changes. One major source of radiation comes from the sun. Solar radiation includes streams of charged particles known as the solar wind, as well as more violent bursts called solar flares and coronal mass ejections. These events can flood space with high-energy protons and electrons capable of damaging electronics and biological tissue. Even within the solar system, spacecraft must be hardened against these events. Astronauts on deep space missions would need shelter zones with additional shielding to ride out intense solar storms. But solar radiation is only part of the picture. Beyond the influence of the sun lies galactic cosmic radiation. These particles originate far outside our solar system, often from supernova explosions and other energetic processes across the galaxy. They travel at near-light speeds and carry enormous energy. Many are heavy atomic nuclei stripped of their electrons, moving fast enough to penetrate significant amounts of material. Cosmic rays are particularly dangerous because they're difficult to shield against. When they strike shielding material, they can generate secondary radiation, showers of particles that spread the damage rather than stopping it cleanly. Adding more shielding does not always help. Sometimes it makes things worse. For biological tissue, cosmic radiation poses several risks. It can damage DNA directly, breaking strands or causing mutations. It can interfere with cellular processes. Over long periods, it increases the risk of cancer, neurological damage, and degenerative diseases. Unlike many environmental hazards, radiation damage accumulates silently. You do not feel it happening. There is no immediate pain to warn you. Over a journey lasting decades or centuries, even low levels of exposure become significant. Then there is dust. Interstellar dust sounds harmless. Dust implies something soft, something that settles quietly on surfaces. In space, dust grains are tiny, often smaller than grains of sand. Individually, they have almost no mass. At everyday speeds, they are irrelevant. At extreme velocities, they become weapons. Kinetic energy increases with the square of velocity. That means doubling speed quadruples impact energy. At a significant fraction of the speed of light, even a microscopic particle carries immense energy relative to the spacecraft. A collision with a grain of dust at those speeds can release energy comparable to an explosive charge. This is not speculation, it is basic physics. Shielding against dust impacts is not as simple as making walls thicker. Thick walls add mass. Mass increases fuel requirements. Fuel requirements grow exponentially with speed. The feedback loop returns. Whipple shields, which use layered structures to break up particles before they reach the main hull, are effective at lower speeds. At relativistic speeds, their effectiveness diminishes. The energy involved is simply too high. Active detection systems could, in theory, identify larger particles ahead of the spacecraft and trigger evasive maneuvers. But at high speeds, reaction times shrink dramatically. A particle detected seconds ahead may already be too late to avoid. At near-light speeds, even detection itself becomes difficult due to relativistic effects and sensor limitations. Dust is sparse, but over interstellar distances, sparse is not the same as rare. Travelling trillions of kilometres through a medium that contains even a few particles per cubic metre guarantees encounters. Over time, probability turns into certainty. Radiation and dust interact in another uncomfortable way. When high-energy particles strike shielding or hull materials, they can knock atoms loose, creating secondary particles and electromagnetic radiation inside the spacecraft. This process slowly degrades materials from the inside out. Metals become brittle, polymers weaken, electronics suffer cumulative damage. This is not catastrophic failure, it is slow decay. Over decades, systems drift out of specification. Sensors lose accuracy, circuits develop faults, insulation breaks down. These changes may be subtle at first, but in an isolated environment, small degradations can compound into serious problems. Now consider electronics more closely. Modern spacecraft rely on complex electronics for navigation, communication, life support, and control. These systems are vulnerable to radiation-induced errors. Single event upsets can flip bits in memory. More severe events can permanently damage components. On Earth and in near-Earth orbit, these risks are mitigated through shielding, redundancy, error-correcting software, and regular updates. In interstellar space, updates must be carried from the beginning. Hardware must survive without replacement. Redundancy helps, but redundancy adds mass, and mass feeds back into every other problem. Even with the best designs, the likelihood of cumulative electronic degradation over centuries is high. Radiation also affects sensors and optics. cameras degrade, lenses darken, detectors lose sensitivity, calibration drifts. Over time, the spacecraft's ability to perceive its environment diminishes. Navigation becomes harder, course corrections become less precise. In deep space, perception is survival. Another quiet danger lies in temperature extremes. Interstellar space is cold, but cold does not mean stable. Without nearby stars, spacecraft rely entirely on internal heat generation and insulation to maintain habitable temperatures. Waste heat must be managed carefully. Too much heat damages systems. Too little allows components to freeze. Thermal cycling occurs as systems operate, shut down and restart. Over long durations, thermal stress contributes to material fatigue. Cracks form, seals fail, mechanical tolerances shift. Again, this is not dramatic. It is gradual. Then there is micrometeoroid erosion. Even tiny impacts can erode exposed surfaces over time. Solar panels degrade, radiators lose efficiency, antennas suffer surface damage, protective coatings wear away. In low Earth orbit, spacecraft experience similar effects, but missions are short enough that degradation remains manageable. Over centuries, erosion becomes a design-defining factor. Every exposed surface must be considered sacrificial or maintainable. Maintenance requires tools, materials, energy, and skilled labour. All of that must be carried from the start. Radiation affects humans and systems differently, but the cumulative effect converges. It increases uncertainty. A mission that must endure decades already faces daunting reliability requirements. A mission that must endure centuries enters territory where statistical failure becomes almost unavoidable. Interstellar space does not actively attack, it simply does not care. There are no safe zones, no natural shelters, no periods of reprieve. The background level of hazard never drops to zero. It remains constant year after year, slowly accumulating damage. This persistence is what makes the danger so difficult to manage. On Earth, hazardous environments are usually localized. You leave them, you rest, you recover. In space, the environment is the same everywhere along the path. There is no exit. This also affects human psychology. Living in an environment where danger is constant but invisible is stressful. There are no storms to prepare for, no alarms that announce threat. The knowledge that radiation is always present, that impacts may occur without warning, that systems are slowly degrading, creates a background tension. This is different from acute danger. It is chronic risk. Studies of long-term isolation show that chronic low-level stress has profound effects on mental health. It erodes resilience, it amplifies conflict, it diminishes motivation, it alters perception and judgment. On an interstellar journey, that stress never ends. The crew cannot step outside to see the stars directly without protection. They cannot feel the environment. They experience it only through instruments and statistics, radiation levels, impact counts, degradation reports. Trust in systems becomes existential. Now consider how these hazards scale with speed. At low speeds, radiation exposure per unit distance remains relatively constant. At higher speeds, relative energies increase, impacts become more energetic, shielding becomes less effective, damage per kilometre travelled increases, speed magnifies hazard. This creates a counterintuitive result. Going faster does not just shorten exposure time, it can increase exposure intensity. The total damage incurred may not decrease as expected. In some regimes, it may increase. This undermines the idea that speed solves environmental risk. Interstellar dust density is low, but its energy relative to the spacecraft scales with velocity. Radiation flux remains, but interaction energies rise. Electronics face more severe events. Biological tissue experiences more complex damage. The environment becomes harsher as you try to outrun it. There is also the problem of unknowns. Our understanding of interstellar space comes from observation and theory, not experience. We have sent a few probes beyond the heliosphere, but none have travelled far into interstellar space. None have operated for centuries. None have carried complex ecosystems. There may be hazards we do not yet fully understand. Subtle variations in particle density, magnetic structures, rare but intense events. Even small uncertainties become significant over long durations. A mission must be robust against what is known and resilient against what is not. That is a tall order. It is tempting to think that future materials will solve these problems. Better shielding, smarter systems, self-healing structures, artificial intelligence managing repairs and adaptations. These advances may help. They will not eliminate the environment. Interstellar space will remain filled with radiation, dust, and energetic particles. Physics does not offer a way to turn it off. At best, you can manage the risk. At worst, you carry it with you. This brings us back to a recurring theme. Each attempt to solve one problem intensifies another. Add shielding to reduce radiation, and mass increases. Increase mass, and fuel demands grow. Grow fuel demands, and exposure time lengthens. Lengthen exposure time and cumulative damage rises. There is no single fix. The dangers of interstellar space are quiet because they operate on long timescales. They do not announce themselves with explosions or dramatic failures. They erode, accumulate, and persist. They reward patience poorly and punish overconfidence. Understanding this reframes the question of interstellar travel yet again. It is not just about getting from one star to another. It is about surviving an environment that offers no assistance, no mercy, and no pause. Strip away the machinery, the equations, the shielding, and the propulsion systems, and what remains at the centre of every interstellar dream is a human body, not a symbol, not an abstraction. A living system built from cells that divide, age, repair themselves imperfectly, and eventually fail. The further and longer a journey stretches, the more this reality asserts itself. Over long voyages, especially those lasting decades or centuries, human biology does not merely face challenges, it becomes the limiting factor. Human bodies evolved under very specific conditions. A steady gravity pulling fluids downward, a day-night cycle that entrains sleep and wakefulness, a narrow range of temperatures, a constant bath of atmospheric pressure and filtered sunlight. Remove or alter these conditions for short periods, and the body adapts surprisingly well. Remove them for long periods, and adaptation gives way to degradation. The clearest example is gravity. Bones exist in a constant conversation with gravity. They grow denser where stress is applied, and lose density where it is not. In microgravity, this conversation changes. Bones no longer need to support weight, so the body conserves resources by breaking bone tissue down. Astronauts can lose 1 to 2% of bone density per month in space, even with aggressive exercise routines. Over a year, that loss becomes clinically significant. Now imagine decades. Even if artificial gravity were created using rotation, which introduces its own complexities, the solution would not be perfect. Rotational gravity varies across the structure. The inner ear experiences Coriolis forces that can cause nausea and disorientation. Long-term effects of growing up in such an environment are still unknown. Bone loss is only one part of the story. Muscles follow the same logic. Without constant resistance, muscle fibers shrink. Strength declines. Endurance drops. Exercise can slow this process, but it requires motivation, time, equipment, and energy. Over long periods, compliance becomes a psychological issue as much as a physical one. The cardiovascular system adapts as well. In microgravity, blood and other fluids shift toward the upper body. The heart does not have to work as hard to pump blood upward. Over time, the heart muscle weakens. Blood pressure regulation changes. Upon returning to gravity, astronauts often experience dizziness or fainting because their bodies have forgotten how to respond. In an interstellar setting, there is no return to Earth to recalibrate. The adapted state becomes the baseline. Then there is the immune system. Spaceflight alters immune function in complex ways. Studies have shown changes in white blood cell behavior, altered cytokine responses, and reactivation of latent viruses during space missions. Stress, radiation exposure, disrupted sleep, and altered circadian rhythms all contribute. A weakened or dysregulated immune system increases vulnerability to infection. In a closed environment, infections spread easily. Microorganisms that are harmless under normal conditions can become dangerous. Antibiotic resistance can emerge. Medical intervention options are limited. Over generations, these effects could interact with genetic drift, altering immune responses in unpredictable ways. Radiation adds another layer of biological stress. Ionizing radiation damages DNA. Cells have repair mechanisms, but they are not perfect. Errors slip through. Mutations accumulate. Cancer risk increases. Neurological effects become more likely. Radiation exposure on Earth is relatively low and stable. In interstellar space, it is higher and more variable. Even with shielding, exposure cannot be eliminated entirely. Over long durations, cumulative doses become significant. For reproductive cells, this is especially concerning. Mutations in germ cells can be passed to offspring. Over generations, mutation rates matter. Even small increases can have large consequences when compounded over time. Developmental abnormalities, reduced fertility, and increased disease risk become possibilities. We do not yet know how human reproduction behaves in environments with altered gravity and elevated radiation. Animal studies provide some insight, but extrapolation to humans across multiple generations remains speculative. Pregnancy itself is sensitive to environmental conditions. Fluid distribution, hormonal regulation, and fetal development are all finely tuned. Disruptions could lead to complications that are manageable on Earth but dangerous in space. Then there is aging. Aging is not a single process. It is a collection of overlapping mechanisms: telomere shortening, accumulation of cellular damage, decline in stem cell function, altered protein folding, mitochondrial dysfunction. Some of these processes may slow under time dilation, but others may not. Radiation damage, for example, depends on exposure, not subjective time. Stress-related aging depends on lived experience, not calendar years. Chronic stress accelerates aging. Isolation, confinement, and constant risk contribute to that stress. Even if the body ages more slowly in some respects, other systems may deteriorate faster. The brain deserves special attention. Neurons do not regenerate readily. Cognitive function depends on complex networks that are sensitive to disruption. Long-term isolation affects mood, attention, memory, and decision-making. Sleep disturbances impair cognitive performance. Radiation exposure may increase the risk of neurodegenerative changes. Over long voyages, maintaining mental health becomes as critical as maintaining physical health. Human brains evolved in environments rich with sensory input. Natural light, changing scenery, social interaction, novelty. In a spacecraft, sensory environments are limited. Views do not change much. Sounds are repetitive. Smells are controlled. Textures are uniform. Monotony is not trivial. It affects neural plasticity. It reduces engagement. It can lead to depression and apathy. These states feed back into physical health by reducing motivation for exercise, self-care, and cooperation. Social dynamics compound the issue. Humans are social animals with complex emotional needs. Long-term confinement with a small group increases the likelihood of conflict. Small disagreements can escalate. Personality differences become magnified. Leadership challenges intensify. Even with careful selection and training, no group remains static over decades. People change. Relationships evolve. Power dynamics shift. Cultural norms drift. Psychological stress affects hormonal balance, immune function, and cardiovascular health. Mental strain becomes physical strain. Sleep is another fragile pillar. Circadian rhythms depend on light cycles. Disruption leads to insomnia, fatigue, mood disorders, and metabolic issues. Artificial lighting can approximate day-night cycles, but perfect alignment is difficult. Over time, desynchronization occurs. Sleep deprivation worsens cognitive function, emotional regulation, and immune response. It accelerates aging. It increases accident risk. In an environment where every mistake matters, impaired sleep is dangerous. Nutrition also interacts with biology in subtle ways. Long-term diets must provide not only calories but micronutrients in correct proportions. Deficiencies may not appear immediately. They can take years to manifest. Bone health, neurological function, and immune response all depend on nutrition. Food variety affects gut microbiota. Changes in microbiome composition influence digestion, immunity, and even mood. In a closed system, microbial ecosystems evolve alongside human ones. Imbalances can have systemic effects that are difficult to predict or reverse. Then there is physical injury. Over long periods, injuries are inevitable. Falls, equipment accidents, repetitive strain. In microgravity or artificial gravity environments, injury patterns differ from Earth. Healing processes may be altered. Bone fractures heal differently in altered gravity. Muscle recovery may be impaired. Infection risk may be higher. Medical intervention capacity is limited. Surgical procedures are more complex in space. Sterility is harder to maintain. Complications are hard to manage. Even a minor injury can become life-threatening without proper support. Consider also developmental biology. Children born and raised in space would develop differently. Their bones, muscles, cardiovascular systems, and sensory processing would adapt to the environment they know. Returning to Earth, if that were even possible, might be physiologically intolerable. This raises ethical questions. Are spaceborne humans still fully compatible with Earth? Would they be able to choose where they live, or would biology constrain them? Even within the spacecraft, developmental differences could emerge between generations, affecting social cohesion and identity. Human biology is not just individual, it is collective and generational. Over long voyages, genetic drift becomes relevant. Small populations are subject to changes in gene frequencies simply due to chance. Certain traits may become more common, others may disappear. Without careful management, this could increase the prevalence of harmful genetic conditions. Managing genetic diversity requires planning, monitoring, and possibly intervention, all of which raise ethical and practical challenges. Stress physiology adds another layer. Chronic stress elevates cortisol levels. Elevated cortisol affects immune function, metabolism, and brain health. Over time, it contributes to cardiovascular disease, depression, and cognitive decline. In a confined environment with constant background risk, stress is difficult to eliminate. Even if acute dangers are rare, the knowledge that failure is catastrophic creates psychological pressure. Humans cope with stress through social support, environmental change, and a sense of control. All three are constrained on an interstellar journey. The fragility here is not weakness, it is specialization. Human bodies are extraordinarily capable within a narrow range of conditions. They are not general-purpose survival machines. They rely on ecosystems, social structures, and environmental stability. When you stretch time and distance far enough, those dependencies become vulnerabilities. This is why discussions of long-duration space travel often turn toward technological fixes for biological limits. Artificial gravity, radiation shielding, genetic modification, cryogenic suspension. Each of these introduces new risks and uncertainties. Altering biology to suit space may solve some problems while creating others. Freezing metabolism may preserve bodies but damage minds. Genetic changes may improve radiation resistance but affect development in unforeseen ways. Biology resists simple solutions. The longer a journey lasts, the more biological uncertainty accumulates. Small unknowns become large risks. Rare events become inevitable. Variability becomes dominant. At some point, it becomes clear that the challenge is not merely keeping humans alive. It is keeping them human in any meaningful sense. This does not diminish the value of human exploration. It reframes it. Perhaps the universe is not meant to be crossed by bodies evolved for planets. Perhaps our role is to explore through tools, through sensors, through machines that do not suffer, age, or reproduce. Machines do not care about bone density. They do not get cancer. They do not experience loneliness. They can be shut down, repaired, duplicated. Humans, by contrast, carry their fragility with them wherever they go. Understanding this is not pessimism, it is clarity. It tells us where our strengths lie and where they do not. It suggests that ambition must be tempered by biology, not because biology is inferior, but because it is precious and specific. Imagine a vessel that does not try to outrun time, but instead accepts it. A structure large enough to hold a community. Gardens under artificial light, rotating sections to simulate gravity, schools, workshops, living quarters, children born aboard, growing up knowing only the interior walls and the distant stars outside reinforced windows. The ship travels slowly, steadily, not expecting its original crew to see the destination. Instead, it passes the mission from one generation to the next. On the surface, this seems like an elegant solution. If the journey to even 1 light year takes centuries at achievable speeds, then let the journey last centuries. Remove the pressure of fitting the mission into a single lifespan. Accept that the travellers will not be the ones who launched. Allow society to move through space the way it moves through history, gradually, continuously. This concept, often called a generation ship, appears to solve one of the most stubborn problems, human lifespan. You no longer need extreme speed. You no longer depend on relativistic time dilation. You no longer need suspended animation. People live, age, reproduce, and pass on knowledge naturally. Biology proceeds as it always has, but solving one problem opens many others. Start with population size. A generation ship cannot carry just a handful of individuals. Small populations are vulnerable to genetic drift, inbreeding, and random catastrophic events. To maintain genetic diversity and long-term viability, the population must be large enough to sustain healthy reproduction over many generations. Estimates vary, but even conservative calculations suggest hundreds, if not thousands, of individuals are necessary to avoid severe genetic bottlenecks. Hundreds of people require enormous infrastructure. Living space alone becomes a major design constraint. Crowding increases stress, conflict, and disease transmission. To maintain mental health and social stability, space per person must be sufficient. This means vast internal volumes, structural mass, shielding mass, and rotational systems if artificial gravity is used. Every cubic meter adds weight. Every kilogram compounds fuel requirements. Then there is food production. A generation ship cannot rely on stored food. It must grow food continuously. That requires agricultural systems robust enough to feed an entire community indefinitely. Hydroponics, aeroponics, soil-based cultivation, or some hybrid system must operate flawlessly for centuries. Agriculture is not simple even on Earth. Crops fail, diseases spread, nutrient cycles shift. Climate variability disrupts yields. On a spacecraft, there is no external environment to buffer these changes. There is no import of new soil or genetic diversity, unless it is carried from the start. Maintaining ecological balance becomes a central mission objective, not a side function. Waste recycling must be nearly perfect. Water must be purified continuously. Nutrients must be recaptured and redistributed. Microbial populations must remain stable. An imbalance in one subsystem can ripple through the entire habitat. Algal blooms, fungal infestations, or bacterial contamination could undermine food supplies or air quality. The ship becomes an artificial planet with none of Earth's redundancy. Governance is another problem that multiplies over time. Who governs a generation ship? The original mission designers? Their authority fades as generations pass. A democratic system. It may evolve in unpredictable ways. A rigid hierarchy. It risks instability if leadership fails or loses legitimacy. Over centuries, political systems change. Revolutions happen, cultural values shift, laws evolve. On Earth, political upheaval can be absorbed regionally. On a spacecraft, instability threatens the entire population. Imagine a faction deciding the mission is no longer meaningful, or that turning back is preferable, or that resources should be used differently. There is no neutral ground to retreat to. Every disagreement is existential. Education becomes critical. Each generation must understand the purpose of the mission, the operation of the ship, and the risks of failure. Knowledge must be preserved accurately. Technical expertise must be passed down reliably. On Earth, information loss over generations is common. Skills disappear when they are no longer practiced. Cultural memory fades. Oral traditions distort. A generation ship must prevent this erosion for centuries. That requires deliberate archival systems, training programs, and cultural reinforcement. Motivation is fragile. The first generation may feel excitement and commitment. They chose the mission. They accepted the sacrifice. Their children did not choose it. Their grandchildren may not even feel connected to Earth as a meaningful concept. For someone born aboard the ship, the journey is not a voyage. It is normal life. The destination may feel abstract, distant, perhaps irrelevant. Maintaining commitment to a goal that lies beyond one's lifetime is difficult. It requires a shared narrative, powerful enough to survive cultural drift. This narrative cannot rely solely on nostalgia for Earth. Earth may become mythologized, misunderstood, or even resented as the place that sent ancestors into confinement. Social stratification presents another challenge. Inequalities in access to resources, education, or authority could emerge over time. Confined environments magnify social tensions. Perceived unfairness can destabilize communities quickly. Resource scarcity exacerbates this. Even with careful planning, unexpected shortages may arise. Energy fluctuations, crop failures, or system degradation could force rationing. Decisions about who receives what become morally charged. Conflicts over resources can escalate rapidly when there is no escape. Mental health must be managed continuously. Long-term confinement, limited social circles, and lack of environmental variation strain psychological resilience. People need novelty, autonomy, and a sense of agency. Providing meaningful roles for every individual across generations requires careful social engineering. Boredom and purposelessness are not minor issues. They can lead to depression, apathy, or rebellion. Reproduction policies become contentious. To maintain stable population levels, births must be regulated. Too many births strain resources. Too few threaten demographic stability. Decisions about who may reproduce and when raise ethical concerns. On Earth, such policies are controversial. On a generation ship, they may be necessary. This introduces questions of autonomy and consent. Are individuals free to make personal choices about family size, or must they adhere to communal survival strategies? How are disputes resolved? Then there is the question of what happens if something goes wrong. On a century-long voyage, accidents are statistically inevitable. Fires, system failures, diseases, or even small mechanical faults can have cascading effects. Redundancy helps, but redundancy increases mass and complexity. Complexity increases failure modes. Unlike a short mission, where systems can be overbuilt for a limited duration, a generation ship must remain flexible and repairable indefinitely. Materials fatigue, bearings wear, circuits degrade. Over centuries, maintenance becomes a way of life. Every generation must be capable of repairing and rebuilding parts of the ship. This requires a broad base of technical expertise and manufacturing capability. It also requires access to raw materials. Where do those materials come from? The ship must carry them or recycle them from existing structures. Mining interstellar space is not practical. There are no convenient resources floating nearby. This makes material management as critical as food management. Cultural drift poses another subtle threat. Over time, language changes, values evolve, historical narratives shift. The original mission objectives may be reinterpreted. A group born into the ship might redefine their purpose. They might decide that living aboard the ship is preferable to reaching an unknown destination. They might abandon the original plan entirely. From an external perspective, this might seem like failure. From their perspective, it could be adaptation. The mission designers cannot control cultural evolution across centuries. Even the destination itself is uncertain. If the target star system proves uninhabitable upon arrival, what then? The generation ship cannot simply turn around. It may not have the resources to alter course significantly. The arrival generation may face disappointment or crisis. Psychologically, this is significant. Imagine dedicating generations of life to a goal that, upon reaching, is unattainable. The emotional impact could destabilize society at the moment it is most vulnerable. Security concerns also arise. With no external oversight, internal threats become critical. Sabotage, negligence, or even simple error can have catastrophic consequences. Systems must be safeguarded not just from environmental hazards but from human behavior. Balancing trust and control is delicate. Too much surveillance erodes morale. Too little increases risk. Then there is the question of death. On Earth, death is buffered by community, ritual, and a broader world that continues unaffected. On a generation ship, every death is visible, personal, and impactful. Cemeteries take space. Resource reclamation may be considered. Cultural practices around death may need to adapt to environmental constraints. These adaptations affect identity and dignity. Finally, consider meaning. Human beings derive meaning from connection, achievement, and future orientation. A generation ship must sustain meaning across individuals who will never see the mission completed. Some may embrace the journey as its own purpose. Others may struggle with the idea of living for a goal beyond their lifetime. Meaning cannot be engineered easily. It must emerge from culture, narrative, and shared experience. Over centuries, those narratives will change. Generation ships solve the lifespan problem elegantly. They allow biology to proceed normally. They avoid the need for extreme speeds or speculative technologies like cryogenic suspension, but they do not eliminate the deeper challenges of distance, isolation, and self-sufficiency. They transform those challenges into social, ecological, and ethical ones. Instead of asking whether engines can function for centuries, we ask whether societies can. Instead of asking whether shielding can block radiation, we ask whether culture can block despair. The solution shifts from physics to sociology, and sociology, like biology, resists simple equations. Understanding this does not render the idea impossible. It makes it clear that a generation ship is not merely a large spacecraft. It is a civilization in transit. Civilizations are fragile. They adapt, fracture, reform, and sometimes collapse. Expecting one to remain stable and focused for centuries inside a sealed structure is asking a great deal. As this complexity unfolds, it becomes clear that the problem of travelling even 1 light year is not a single obstacle. It is a web of interlocking constraints. If you solve for lifespan, you create social strain. If you solve for speed, you magnify energy and hazard. If you solve for isolation, you increase mass. If you reduce mass, you sacrifice redundancy. Every solution tilts the balance somewhere else, and yet the desire to bridge that distance persists. Perhaps not by carrying entire societies across the void, perhaps by rethinking what it means to travel at all. There is a certain appeal to the idea of simply skipping the hard part. If time is the problem, then don't experience it. If biology breaks down over decades, then pause it. If boredom, aging, conflict and resource consumption threaten a long journey, then remove consciousness from the equation altogether. Let the ship travel while its passengers sleep, untouched by years, drifting quietly through the dark until arrival. Suspended animation sounds almost merciful. It promises a way around many of the difficulties that plague long voyages. No need to maintain morale, no need to educate generations, no need to support a complex society in a closed environment. Fewer calories consumed, less water used. Reduced wear on life support systems. From a distance, it looks like an elegant shortcut, but the closer you look, the more that shortcut dissolves. The first problem is definitional. Humans already sleep, but sleep is not suspension. During sleep, the brain remains active, metabolism continues. Cells repair themselves, hormones are released, memory is processed. Even in deep sleep, the body is very much alive and busy. Suspended animation, as imagined for interstellar travel, would require something far more extreme. Metabolism would need to slow dramatically, perhaps by orders of magnitude. Cellular activity would need to pause without causing damage. The brain would need to retain memory, identity and function despite long periods of inactivity. Nature offers a few partial examples. Some animals hibernate, others enter states of torpor. Certain organisms can survive freezing or dehydration by shutting down most biological processes, but humans are not among them. Hibernation in mammals involves complex physiological changes. Heart rate slows, body temperature drops, metabolism decreases. Even so, hibernating animals periodically wake up. They cycle through phases of torpor and arousal. These arousals appear necessary to prevent neurological damage and maintain immune function. Humans do not hibernate naturally. Inducing a similar state artificially would require overriding deeply ingrained biological systems. Experiments in medical hypothermia show that lowering body temperature can slow metabolism and protect tissues during trauma or surgery, but these states are temporary and carefully controlled. Prolonged hypothermia carries risks. Blood clotting changes, immune function is suppressed, infection risk increases, electrolyte balance becomes unstable, organs can suffer damage, and hypothermia is still not true suspended animation. It slows processes, it does not stop them. Cryogenic freezing pushes further. Freezing biological tissue introduces a new set of problems. Water expands when it freezes, forming ice crystals that puncture cell membranes and disrupt internal structures. Cryoprotectants can reduce ice formation, but they are toxic in high concentrations. Achieving uniform cooling and warming without damage is extraordinarily difficult. At small scales, some cells and tissues can be frozen and revived. Whole organs are far more challenging. Entire human bodies, with complex interconnected systems, remain far beyond current capabilities. Even if freezing were possible without immediate structural damage, revival presents another hurdle. Rewarming must be perfectly controlled. Metabolic processes must restart in the correct sequence. Immune responses must not overreact. The brain must resume function without losing memory or personality. We do not know how to do this. Even more concerning is what happens during long storage. Radiation does not stop just because metabolism slows. DNA damage can still occur. Over centuries, even low levels of radiation could accumulate mutations in frozen tissue. Repair mechanisms are inactive during suspension. Damage accumulates silently. This creates a paradox. Suspending metabolism protects against aging, but may increase vulnerability to other forms of damage. Then there is the brain. Human identity is encoded in patterns of neural connections, electrical activity, and biochemical states. Memory is not stored like data on a hard drive. It is dynamic. It depends on ongoing cellular maintenance. We do not know whether a brain can be completely shut down for decades or centuries and resume function unchanged. Small disruptions could lead to memory loss, personality changes, or cognitive impairment. Even partial loss would raise profound ethical questions. If a person wakes up without memories of who they were, are they the same individual? If personality shifts occur, who consented to the journey? Consent itself becomes complicated. A person may agree to suspended animation for a long journey, understanding the risks. But if revival leads to cognitive impairment or psychological change, that consent becomes murky. The person who wakes may not be the same person who agreed. Now consider system reliability. Suspended animation does not eliminate the need for life support systems. It changes their requirements, but it does not remove them. Temperature control must remain stable. Radiation shielding must remain intact. Monitoring systems must detect failures. Power must be supplied continuously. A failure that might be survivable for an awake crew could be fatal for a sleeping one. There is no one to respond immediately. Automated systems must handle every contingency. Automation helps, but automation is not infallible. Software errors occur, sensors fail, unexpected interactions emerge. Over long durations, the probability of uncorrected failure rises. Redundancy mitigates risk, but redundancy adds mass and complexity. Complexity increases failure modes. Suspended animation also changes the nature of emergencies. If something goes wrong while the crew is awake, they can intervene, improvise, and adapt. If something goes wrong while they are suspended, intervention may come too late. Who wakes the crew? Under what conditions? How quickly? What if the systems responsible for revival are damaged? Then there is the psychological dimension of waking. Imagine opening your eyes after decades or centuries. The world you knew is gone. Everyone you loved is long dead. Earth has changed beyond recognition, assuming it still exists in any meaningful sense. You arrive not just in a new place, but in a new era. This shock is not trivial. Even astronauts returning from months-long missions report difficulty reintegrating. Their sensory expectations differ. Social rhythms feel strange. Multiply that effect by orders of magnitude. There is also the question of purpose. If suspended animation reduces the journey to a subjective blink, what happens to meaning? Human lives are structured by experiences. Growth, struggle, learning, adaptation. Sleeping through the journey bypasses these processes. You arrive having skipped a vast portion of time. You did not live it. You endured it passively. Some might find this acceptable, others might not. Then consider children. Suspended animation does not solve reproduction. You cannot freeze unborn generations. Someone must be awake to maintain systems, to monitor conditions, to manage unexpected events. This raises the idea of rotating crews, some awake, some asleep. But this reintroduces social complexity, inequality of experience, unequal aging, power imbalances between those who age and those who do not. Who decides who sleeps and who stays awake? For how long? Under what conditions? These are not technical questions, they are ethical and social ones. Suspended animation also assumes that the destination is ready. If the crew sleeps until arrival, they wake at a moment of maximum vulnerability. They must immediately assess an unknown environment, manage landing or orbital insertion, and respond to potential hazards, all while coping with physical and psychological after effects of suspension. Any delay in recovery could be dangerous. Moreover, the destination itself may not be what was expected. Conditions may differ. The target planet may be uninhabitable. Infrastructure may not exist. Plans may need revision. A waking crew must be capable of rapid adaptation. Suspended animation does not guarantee that. There is also a deeper biological issue. Life is not just a collection of parts, it is a process. Many biological systems rely on continuous activity to maintain integrity. Muscles, bones, neural circuits, immune surveillance, and cellular repair all depend on ongoing feedback loops. Interrupting those loops for long periods risks destabilizing the system. We do not yet understand which processes can safely pause and which cannot. The body is not a machine that can be powered down cleanly. Medical science has made remarkable progress in extending life, slowing certain processes and protecting tissues under extreme conditions. It has not shown that long-term, whole-body suspension with full recovery is possible. Even if it were, scaling it to many individuals, maintaining it for centuries, and ensuring safe revival would be an unprecedented challenge. Suspended animation also interacts poorly with uncertainty. Long journeys are unpredictable. New hazards emerge. Systems degrade in unexpected ways. Missions require adaptability. A sleeping crew cannot adapt. They rely entirely on pre-programmed responses. Artificial intelligence could help, but AI systems also degrade, require updates, and operate within the limits of their design assumptions. If the journey deviates significantly from plan, a suspended crew may awaken to find themselves in an irrecoverable situation. In that sense, suspended animation trades active risk for latent risk. The danger is not constant, but when it appears, it is concentrated. This is why, despite its appeal, suspended animation remains speculative. It is not merely a technological hurdle, it is a fundamental challenge to how human biology functions. Sleep evolved as a restorative process within a stable environment. It was not designed as a means of skipping centuries. When extended beyond its natural role, sleep stops being rest and starts becoming erasure. That may sound dramatic, but it reflects a real concern. The longer you pause biological processes, the more you risk losing what made them coherent in the first place. Suspended animation solves the problem of waiting. It reduces resource consumption. It sidesteps boredom and aging, but it does not solve the problem of fragility. It concentrates risk into fewer moments. It assumes perfect systems, perfect preservation, and perfect revival. And perfection is rare. As with other proposed solutions, suspended animation shifts the problem rather than eliminating it. It exchanges continuous strain for catastrophic vulnerability. Shift the frame slightly, and a different possibility comes into view. Instead of asking how to make human bodies survive interstellar travel, ask whether human bodies need to make the journey at all. That question feels unsettling at first, almost like a retreat. But it is also practical. Machines do not share many of the vulnerabilities that dominate every previous discussion. They do not age biologically. They do not require air, food, or sleep. They do not suffer boredom or loneliness. They can endure radiation better than living tissue. They can wait without complaint. So perhaps the answer is not to carry people across a light year, but to send machines in their place. At a basic level, this is already happening. Humanity explores the universe primarily through machines. Telescopes observe distant galaxies. Probes travel to planets and moons. Rovers traverse alien surfaces. Data returns to Earth, where human minds interpret it. Presence is extended through instruments rather than bodies. Extending this approach to interstellar distances feels like a natural progression. A robotic probe does not care if the journey takes decades or centuries. It does not require a large habitat. It can be small, lightweight, and efficient. It can be designed for a specific purpose and nothing more. This immediately reduces mass, which reduces fuel requirements, which reduces exposure time and hazard. Many problems simply shrink when the payload is not human. But this is not the end of the story. Machines may solve biological constraints, but they introduce a different set of challenges. Some are technical, others are philosophical, still others blur the line between the two. Start with endurance. A machine sent across interstellar space must operate for extremely long periods, not just in transit, but upon arrival. Systems must survive radiation exposure, micrometeoroid impacts, thermal cycling, and gradual material degradation. On Earth, Machines are maintained continuously. Parts are replaced. Software is updated. Components are redesigned when weaknesses are discovered. An interstellar probe receives none of that. Every system must be designed to function correctly for decades or centuries without intervention. Redundancy helps, but redundancy adds mass and complexity. Complexity increases failure modes. Even simple machines fail eventually. Bearings wear. Lubricants break down. Electronic components suffer radiation damage. Memory degrades. Sensors drift. Actuators seize. Some of these issues can be mitigated with careful design. Solid-state components instead of moving parts. Radiation-hardened electronics. Self-checking software. Error correction. But nothing operates forever. Then there is the question of autonomy. An interstellar machine cannot rely on constant guidance from Earth. Communication delays measured in years make real-time control impossible. The machine must make decisions on its own. This requires artificial intelligence or advanced automation capable of handling unexpected situations. Navigation errors, environmental anomalies, system failures. Automation can be extremely reliable within well-defined boundaries. It struggles when conditions fall outside expected parameters. Interstellar space and unknown star systems are, by definition, outside our direct experience. Designing a machine that can adapt safely to truly unknown environments is an unsolved problem. Artificial intelligence introduces additional complexity. AI systems learn, but learning requires data. They generalize, but generalization can fail in edge cases. They optimize objectives, but poorly defined objectives can lead to unintended behavior. In a closed system, unintended behavior can be catastrophic. Then there is the matter of repair. If a machine breaks, who fixes it? Self-repair is an attractive concept. A probe could carry spare parts, raw materials, and manufacturing tools. It could diagnose faults and fabricate replacements. This requires a high degree of complexity. Manufacturing in space is difficult. Precision assembly without human oversight is still limited. Quality control becomes a challenge. Errors in self-repair could compound over time, degrading the system rather than restoring it. Another approach is redundancy through numbers. Instead of one complex probe, send many simpler ones. If some fail, others succeed. This strategy is robust, but it has limits. Each probe still requires propulsion, communication, and power. The total mass increases. Launch costs rise. Communication itself is not trivial. An interstellar probe must send data back across light years. This requires power. Transmitters must operate reliably. Antennas must remain aligned. Signals weaken with distance. Data rates drop. At large distances, transmitting even small amounts of data becomes energy intensive. A probe may spend most of its available power simply sending information home. Power generation becomes critical. Solar power diminishes rapidly with distance from stars. Beyond the outer regions of a solar system, sunlight becomes too weak to rely on. Nuclear power sources become necessary. Radioisotope generators provide steady power for decades, but their output declines over time. Fission reactors could supply more power, but they add complexity and mass. They also introduce heat management challenges. Fusion power remains speculative. Energy storage degrades. Batteries lose capacity. Capacitors fail. Power management systems must operate flawlessly. Then there is navigation and targeting. Stars move relative to each other. Over decades or centuries, their positions shift. A probe launched toward a target star must account for this motion precisely. Small errors early in the journey magnify over time. Course corrections require propulsion. Propulsion requires fuel or interaction with external forces. A probe cannot simply coast and hope for the best. Even upon arrival, challenges continue. The probe must identify planets, characterize environments, avoid hazards, and select targets of interest. It must prioritize data collection and transmission. It must operate in environments we have never encountered. If the probe fails after arrival, the mission fails completely. This raises an uncomfortable question. If machines can make the journey but humans cannot, what does that say about exploration? Are we content to explore vicariously forever? To receive images, measurements and spectra, but never feel a foreign sky overhead? Never stand on alien ground? Some argue that presence matters, that there is something irreplaceable about being there. Others point out that instruments already see more than human senses ever could. They detect wavelengths invisible to our eyes. They measure particles and fields we cannot feel. Perhaps presence is a story we tell ourselves. There is also the idea of sending information instead of matter. Rather than sending a physical probe, send the blueprint for one. Transmit data to a destination where machines could assemble structures using local materials. This requires infrastructure at the destination, which does not exist unless placed there earlier. It assumes the ability to receive, interpret, and act on instructions. It also assumes that information alone is enough. Then there is the idea of sending minds instead of bodies. If human consciousness could be digitized, copied, and transmitted, perhaps the journey could be outsourced to machines carrying data rather than flesh. This concept opens a different set of questions. We do not know whether consciousness can be separated from biology in this way. Even if it could, issues of identity, continuity, and ethics arise. Is a copy the same person? What happens if multiple copies exist? Who consented? Even if such questions were resolved, the technology remains speculative. Returning to more grounded considerations, machines still face the same physical environment as humans. Radiation, dust, and time degrade them. They are more tolerant but not immune. A machine can wait patiently, but patience does not prevent failure. There is also the issue of purpose. Machines do not have goals of their own. They execute programmed objectives. Over long durations, those objectives may become obsolete. New questions may arise that the original mission did not anticipate. Without the ability to redefine purpose dynamically in a human sense, a machine's exploration may be limited by the assumptions baked into it at launch. Artificial intelligence could, in theory, adapt objectives based on new information. But then control becomes ambiguous. Who decides what the machine should prioritize? How much autonomy is acceptable? Trust becomes central. Sending a machine across interstellar space is an act of trust in its design, its software, and its decision-making framework. Once launched, that trust cannot be revoked easily. There is also the symbolic dimension. Human exploration has always been tied to stories of courage, risk, and presence. Machines exploring in our place shifts that narrative. It reframes exploration as observation rather than participation. This is not necessarily worse, it is different. From a practical standpoint, outsourcing the journey to machines appears to be the only approach that scales realistically with distance. Machines are lighter, more tolerant, and more flexible than human bodies. From an emotional standpoint, it leaves something unresolved. The desire to go is not purely rational. It is tied to identity, curiosity, and meaning. Sending machines satisfies curiosity. It does not satisfy the longing for presence. This tension runs through every serious discussion of interstellar travel. We know how to send machines far beyond where humans can go. We're already doing it. We do not know how to send humans safely across even 1 light year. That gap may never close, or it may close only by changing what we mean by human. Machines may be the scouts, the messengers, the first arrivals. They may map star systems, analyze planets, and send back knowledge. Humans may remain bound to planets, reaching outward through tools rather than bodies. This is not a failure. It may be an adaptation. Yet even machines do not escape all limits. Energy still constrains them. Propulsion still matters. Distance still exacts a toll. As promising as machines are, they do not erase the fundamental challenge. They navigate it more gracefully, but they still operate under the same physical laws, and those laws impose another boundary that has not yet been examined directly: energy. Energy is easy to take for granted when it arrives silently through outlets in the wall or fuel flowing from a pump. It feels abstract, almost infinite, because the systems that produce it are far away and mostly invisible. For interstellar travel, energy stops being background infrastructure and becomes the central obstacle. Not one challenge among many, but the wall every other idea eventually runs into. This wall is not metaphorical, it is numerical. It is enforced by conservation laws that have never been violated, and it does not care how clever a design looks on paper. Every attempt to move anything across interstellar space must pay an energy cost. That cost comes from two sources: accelerating mass and sustaining systems over time. Both grow rapidly as ambitions increase, both compound each other, start with motion itself. To move a spacecraft from rest to some velocity requires kinetic energy. The formula is simple at everyday speeds, but it becomes brutal as velocity increases. Even ignoring relativistic effects for a moment, kinetic energy scales with the square of velocity. Doubling speed requires 4 times the energy. Increasing speed by a factor of 10 requires 100 times the energy. Interstellar distances demand enormous speeds if travel time is to remain remotely meaningful. That alone pushes energy requirements far beyond anything we routinely handle. Consider a modest-sounding target, 10% of the speed of light. This is not relativistic travel in the dramatic sense. It is still far below light speed. At that velocity, 1 light year takes about 10 years from the traveller's frame, ignoring acceleration and deceleration. Reaching that speed with even a small spacecraft requires staggering energy. Take a spacecraft with a mass of just 1,000 metric tons. That is tiny by generation ship standards, but large enough to carry shielding, systems, and payload. Accelerating that mass to 10% of light speed requires on the order of 4.5 times 10 to the 18th power joules of kinetic energy. That number is hard to grasp, so translate it. Humanity's total annual energy consumption is roughly 6 times 10 to the power of 20 joules. Accelerating this one small spacecraft would consume close to 1% of all energy used by the entire human civilization in a year. That is just acceleration. Now add deceleration. You must spend a similar amount of energy to slow down when you arrive, unless you are content to pass through the destination system at enormous speed and continue into the dark. So double the number, now add inefficiencies. No propulsion system converts energy into motion with perfect efficiency. Some energy is lost as heat, some is lost as waste radiation. Some goes into accelerating fuel that never contributes directly to payload motion. The real energy requirement climbs higher. Now consider scaling up. 1,000 tons is not enough for a crude interstellar mission with redundancy, shielding, and life support. A more realistic mass might be tens of thousands of tons or more. Multiply the energy accordingly. At this point, the energy requirement for a single mission begins to rival the output of entire nations over many years. And this still ignores the cost of building the spacecraft, producing the fuel, and constructing the infrastructure needed to generate and manage such energy. Chemical energy cannot reach these levels efficiently. Nuclear fission improves matters, but not nearly enough. Fusion, if it can be made practical, offers higher energy density, but still faces immense engineering challenges. Antimatter is often invoked as the ultimate energy source. Matter-antimatter annihilation converts nearly all mass into energy. In theory, it is the most efficient process imaginable. In practice, antimatter is extraordinarily difficult to produce. Creating even a gram requires enormous amounts of energy. Current production rates are measured in nanograms per year, at astronomical cost. Storing antimatter safely for long periods is another challenge entirely. Even if antimatter propulsion were perfected, the energy accounting does not disappear. You still need to generate that antimatter using conventional energy sources. The energy wall simply moves upstream. Energy generation itself becomes the next barrier. On Earth, large-scale energy production relies on vast infrastructure. Power plants, transmission grids, fuel supply chains, cooling systems, maintenance crews. All of this exists within a planetary environment rich in resources and redundancy. Interstellar spacecraft cannot rely on planetary-scale infrastructure. They must either carry their energy with them or harvest it along the way. Carrying energy means fuel. Fuel adds mass. Mass increases energy requirements. The loop tightens again. Harvesting energy in space is difficult. Solar power falls off rapidly with distance from stars. Beyond the inner regions of a solar system, sunlight becomes too weak to be useful at scale. Interstellar space offers no ambient energy source dense enough to exploit easily. Some concepts propose collecting energy over long periods before launch. Build enormous laser arrays. Store energy in massive flywheels or other storage systems. Use that stored energy to push spacecraft gradually. These ideas are not impossible in principle. They are immense in scale. A laser array capable of accelerating a light sail to significant fractions of light speed would need to be kilometers wide, perhaps larger. It would require power outputs comparable to the output of large power plants, sustained over long durations. It would require extreme precision in aiming and control. Building such infrastructure is itself a planetary scale project, and that infrastructure would serve a single launch direction. Adjusting targets requires reconfiguration. Maintenance must be constant. Failures could be catastrophic. Energy storage presents another challenge. Storing large amounts of energy safely is difficult. Batteries have limited energy density and degrade over time. Chemical storage is bulky. Nuclear storage introduces safety concerns. Flywheels require materials capable of withstanding enormous stresses. Energy wants to move. Keeping it contained safely for long periods is never trivial. Then there is heat. Every energy conversion process produces waste heat. In space, heat can only be removed by radiation. Radiators must be large to dissipate significant power. Large radiators add mass and surface area. Surface area increases vulnerability to radiation and dust impacts. As power levels rise, thermal management becomes a dominant design constraint. High-energy systems must also be controlled precisely. Sudden releases of energy can damage structures. Gradual leaks can degrade systems. Safety margins must be large. Safety margins add mass. The energy wall is not just about producing enough energy. It is about managing it without destroying the vehicle or its occupants. Now consider time again, but from an energy perspective. Long journeys require sustained power for life support, computation, communication, and maintenance. Even if propulsion energy was somehow solved, operational energy remains. A crewed spacecraft must generate power continuously for decades or centuries. That power must be reliable. Interruptions are not acceptable. Nuclear reactors could provide steady power, but reactors have finite fuel lifetimes. Refueling is not possible unless fuel is carried. Carrying fuel adds mass. Reactors also require cooling systems, shielding and maintenance. Radioisotope generators decay over time. Their output decreases. Planning for declining power adds complexity. Every watt must be budgeted carefully. Communication energy also scales poorly. Transmitting signals across light years requires significant power. Signals weaken with distance. Data rates drop unless transmission power increases or antenna size grows. Large antennas add mass. High transmission power adds thermal load. A spacecraft far from Earth may spend much of its available energy budget simply communicating. Now step back and look at the broader picture. The energy wall is not a single cliff. It is a slope that steepens relentlessly. Each step forward demands disproportionately more energy than the last. Gains become harder. Costs grow faster. This is why incremental improvements do not bridge the gap. Improving engine efficiency by 10% helps with planetary missions. It barely moves the needle for interstellar travel. Doubling efficiency helps more, but still not enough. Orders of magnitude are required. Those orders of magnitude must come from fundamentally new ways of producing, storing, and using energy. And even then, the wall does not disappear. It recedes slightly. There is also a political and social dimension to energy. Energy production at planetary scale is tied to economics, environmental impact, and governance. Diverting a significant fraction of a civilization's energy output to a single interstellar mission raises questions of priority. What else could that energy be used for? Climate mitigation, healthcare, infrastructure, education, exploration closer to home. Interstellar travel competes with all of these. Even if technically feasible, it may not be socially acceptable to allocate such enormous resources to a venture with uncertain return. This matters because technology does not exist in isolation. It exists within societies that decide what to build and why. The energy wall is therefore not just physical, it is contextual. Now consider the asymmetry. The energy required to move mass across interstellar space is enormous. The energy required to observe distant stars remotely is comparatively tiny. Telescopes, sensors, and probes offer a far better return on energy investment. This asymmetry shapes exploration choices. It is far cheaper to look than to go. That is not a limitation of imagination. It is a rational response to energy economics. One might imagine future civilizations with vastly greater energy resources. Perhaps they harness the full output of their star. Perhaps they build structures that capture stellar energy at scale. Even then, the wall remains relevant. Capturing stellar energy requires massive structures. Building and maintaining them requires energy and materials. Using that energy for propulsion still faces the same physical laws. A civilization that can easily move starships at relativistic speeds would have to be orders of magnitude more advanced than ours. It would operate on scales that dwarf anything we currently imagine. At that point, the question of why to travel becomes as important as how, because a civilization capable of such feats could likely achieve most goals without sending physical beings across space. The energy wall forces a reckoning. It asks whether interstellar travel is something we cannot do yet, or something that is fundamentally inefficient given the alternatives. Understanding this wall reframes ambition. Instead of asking how to climb it, some begin to ask whether it is worth climbing at all. This does not mean exploration ends, it means exploration takes different forms. Observational astronomy becomes more powerful, remote sensing improves, simulation and modelling grow more sophisticated, probes become more capable, knowledge expands without mass movement. The desire to go remains, but it is tempered by cost. Energy is the currency of the universe. It is conserved. It must be paid. There are no shortcuts. Every previous obstacle discussed, distance, speed, fuel, biology, radiation, social complexity, ultimately funnels into this one. Energy underlies them all. If you cannot supply enough energy, nothing else matters. If you can, other problems still remain, but at least they can be addressed. At present, we cannot supply enough. That is not a failure of will. It is a statement of scale. Recognizing the energy wall clarifies why even 1 light-year remains out of reach. It is not just far. It is energetically expensive in a way that challenges the foundations of our technological civilization. Nothing in the laws of physics stands up and says no. That is what makes this question so persistent. There is no single equation that slams the door shut. No universal speed bump labelled interstellar travel prohibited. Instead, physics does something more subtle and far more frustrating. It permits the journey in principle while arranging the conditions so harshly that, in practice, the journey slips out of reach. This difference between permission and feasibility is easy to miss. Physics describes what is allowed. Reality is where allowed things must actually happen. From a purely theoretical standpoint, travelling 1 light-year is possible. Objects can move through space. Energy can be converted into motion. Time dilation exists. Matter can survive radiation up to certain limits. None of these facts contradict the idea of interstellar travel. In textbooks and equations, the path remains open. But reality is not a textbook. It is a system where every variable interacts with every other variable, where margins matter, and where small inefficiencies accumulate until they dominate the outcome. Physics says the trip is allowed. Reality quietly refuses to make it affordable, reliable, or survivable. Start with the most important distinction. Physics deals in idealized conditions. Reality never does. In physics, engines are often assumed to operate at ideal efficiency. In reality, every engine loses energy to heat, vibration, and waste. In physics, materials are often assumed to be perfect. In reality, materials fatigue, crack, corrode, and degrade. In physics, systems are isolated neatly. In reality, everything interacts with everything else. Those imperfections are manageable at small scales. They become decisive at interstellar ones. The equations that allow high-speed travel do not account for manufacturing tolerances, maintenance schedules, political instability, funding cycles, or human error. They do not account for software bugs, sensor drift, or unforeseen interactions between systems. They assume that what can be built once can be built perfectly and maintained forever. Reality has never behaved that way. Take propulsion as an example. Physics allows a rocket to accelerate to a significant fraction of the speed of light. There is no forbidden symbol in the equations. But reality demands that the rocket be built from real materials, powered by real energy sources, and operated for real durations. Each of those requirements introduces friction. Fuel must be mined, processed, transported, and stored. Engines must withstand enormous temperatures and stresses. Structures must survive vibration and radiation. Control systems must function without interruption. Over years, these challenges are difficult. Over centuries, they become overwhelming. Physics allows time dilation to reduce subjective travel time. Reality introduces asynchronous communication, social disconnection, and mission irrelevance. Physics allows suspended animation in speculative models. Reality offers no proven method to pause a human mind and body safely for decades or centuries. Physics allows generation ships. Reality demands flawless social systems, perfect ecological balance, and cultural stability across timescales longer than any human civilization has ever demonstrated. At every turn, the laws of physics remain permissive. Reality keeps adding footnotes. Another critical difference lies in scale. Physics scales smoothly. Reality does not. An experiment that works on a laboratory bench does not always work at industrial scale. A system that functions for hours does not necessarily function for years. A process that works in isolation may fail catastrophically when integrated into a larger system. Interstellar travel requires scaling nearly every human technology to extremes simultaneously. Energy generation must scale. Energy storage must scale. Materials science must scale. Autonomy must scale. Reliability must scale. Social organization must scale. Scaling one domain is hard. Scaling all of them together is unprecedented. On Earth, complex systems survive because they are supported by redundancy across space and time. If one power plant fails, others compensate. If one institution collapses, others persist. If one technology becomes obsolete, another replaces it. An interstellar mission has none of this redundancy. It is a single, isolated system moving through an environment that offers no assistance. There are no replacement parts floating between stars, no emergency services, no trade networks, no external corrections. Physics does not forbid isolation. Reality punishes it. This brings us to probability. Physics often deals in deterministic relationships. If you apply this force, you get that acceleration. If you expend this energy, you reach that speed. Reality is probabilistic. Components have failure rates. Materials have lifetimes. Humans make mistakes. Over short durations, probabilities can be managed. Over long durations, probabilities compound. A system with a 99.9% annual reliability sounds excellent. Over 1 year it is. Over 10 years, cracks begin to appear. Over 100 years, failure becomes likely. Over 1,000 years, failure becomes almost certain. Interstellar journeys stretch directly into this probabilistic danger zone. Physics does not care how long a system operates. Reality does. Every additional year is another roll of the dice. Another chance for something to go wrong. Another opportunity for entropy to assert itself. Entropy is not dramatic. It does not explode or announce itself. It erodes. Bolts loosen, seals degrade, calibration drifts, documentation becomes outdated, skills atrophy. Institutional memory fades. On Earth, entropy is countered by constant effort. Maintenance crews, inspectors, upgrades, redesigns. All of that requires resources and coordination. In deep space, entropy accumulates unchecked. Physics allows perfect insulation. Reality leaks heat. Physics allows perfect shielding. Reality leaves gaps. Physics allows perfect planning. Reality introduces unknowns. The environment itself adds another layer. Interstellar space is not hostile in a cinematic way. It is hostile in a statistical one. Radiation levels are low but persistent. Dust density is sparse but non-zero. Thermal gradients are manageable but constant. Physics models these hazards as averages. Reality delivers them as events. A single high-energy particle can flip a bit in memory. A single micrometeoroid can damage a critical surface. A single unexpected solar event can overwhelm shielding. None of these events violate physical laws. They simply exploit the margins. As margins shrink, vulnerability grows. Interstellar travel shrinks margins everywhere. Fuel margins, energy margins, psychological margins, social margins, maintenance margins. There is very little room for error. Then there is the issue of opportunity cost. Physics does not consider alternatives. Reality does. A civilization capable of launching an interstellar mission must decide how to allocate its resources. The energy, materials, and labor required for such a mission are enormous. Those same resources could be used for other goals. Improving life on the home planet, expanding infrastructure, advancing medicine, exploring the solar system more thoroughly, building better observational tools. Interstellar travel competes with all of these. Physics says you can climb the energy wall. Reality asks why you would choose to when the view from below is already extraordinary. This is not a trivial consideration. Technological civilizations do not pursue every possible project. They pursue projects that offer favorable returns on investment, whether that return is knowledge, security, prosperity, or meaning. At present, interstellar travel offers poor returns relative to cost. That may change, but physics does not guarantee that it will. Another subtle refusal comes from timescales. Physics is indifferent to time. A process that takes a second and one that takes a millennium are both acceptable. Reality is not indifferent. Human institutions struggle to maintain continuity for centuries. Funding priorities shift. Political systems change. Cultural values evolve. Long-term projects are vulnerable to disruption. Even projects spanning a few decades require extraordinary coordination and stability. Interstellar missions demand stability across generations. This is not impossible, but it is rare. The further a project extends into the future, the more assumptions it makes about continuity. Those assumptions accumulate risk. Physics allows a 1,000-year mission. Reality struggles to support one. There is also the matter of feedback. Short missions benefit from rapid feedback. Problems are identified and corrected. Designs are refined. Lessons are learned. Long missions do not. An interstellar mission launched today may not provide meaningful feedback for centuries. By the time data returns, the people who designed the system are long gone. The technologies used may be obsolete. The context may have changed. This makes iterative improvement difficult. Physics allows a first attempt to succeed eventually. Reality relies on iteration to achieve reliability. Without iteration, mistakes persist. All of this leads to an important conclusion. Interstellar travel sits in a region where physics is permissive but unforgiving, and reality is constrained but adaptive. Physics says yes, but only under extreme conditions. Reality says no, not because it is impossible, but because it is inefficient, fragile, and misaligned with how human systems operate. This distinction matters. It means that interstellar travel is not a forbidden dream. It is an impractical one given current constraints. It also means that breakthroughs alone may not be enough. A new propulsion system does not solve social instability. A new energy source does not solve maintenance over centuries. A new material does not solve motivation across generations. The refusal comes from the combination. Reality is a multivariable system. Physics describes each variable separately. When combined, the space of workable solutions shrinks dramatically. This is why discussions of interstellar travel often feel tantalizing but unresolved. Each piece seems solvable in isolation. Together, they resist integration. Understanding this does something useful. It shifts the conversation away from frustration and toward perspective. If the universe does not easily allow beings like us to cross between stars, that may not be an oversight. It may be a clue about scale. Stars are not cities separated by highways. They are islands separated by oceans so vast that even light takes years to cross them. Life may be common. Travel between life-bearing worlds may be rare. Civilizations may observe one another across space rather than meet physically. Knowledge may spread through light rather than ships. In that context, the difficulty of interstellar travel is not a failure. It is a feature. It encourages inward development and outward observation rather than expansion by migration. It favors patience over conquest. It suggests that the universe is built to be seen more easily than crossed. Physics allows the trip because the universe is consistent and lawful. Reality refuses it because consistency alone does not guarantee practicality. The laws do not bend to desire. They simply wait to be obeyed. If 1 light year remains beyond our reach, what does that tell us about where we are and what we should value? Stand back from the equations for a moment, and the question changes shape. After all the calculations, constraints, and quiet refusals, what remains is not just a technical problem, but a lesson. 1 light year is not merely a distance we struggle to cross. It is a boundary that teaches us something about who we are and how the universe is arranged around us. Human intuition evolved at planetary scales. Our ancestors measured distance by how far they could walk in a day, how long it took the sun to cross the sky, how many seasons passed between planting and harvest. Even our most ambitious historical journeys fit within these rhythms. Oceans could be crossed in months, continents in years. The world, though large, felt connected. A light year breaks that connection. It introduces a scale where everyday intuition no longer applies, where effort does not map cleanly to reward, and where progress stretches beyond individual lives. When we confront that scale honestly, we are forced to confront our own size, not just physically, but temporally and culturally. The universe is not built to center us. This is not a new idea, but it arrives with renewed clarity when distance is taken seriously. Earth is not positioned at a crossroads of easy travel. Our star is not embedded in a dense cluster of neighbours. We are not located in a region where moving between stellar systems is a natural extension of daily activity. Instead, we inhabit a galaxy where stars are separated by enormous gulfs of emptiness. Those gulfs are not accidental. They are a direct consequence of how matter behaves, how gravity organizes large-scale structure, and how energy flows over cosmic time. The spacing between stars reflects the balance between gravitational attraction and the expansion of the universe, shaped over billions of years. In other words, the difficulty of interstellar travel is not a design flaw. It is a natural outcome. Recognizing this reframes humanity's role. We are not explorers in a universe laid out like a map of nearby towns. We are observers embedded in a vast, sparsely connected system. Our strength is not physical reach, but perception. This has already shaped how we learn. We do not study distant stars by visiting them. We study them by collecting their light. We decode information carried across space at the fastest speed nature allows. Telescopes extend our senses far beyond the reach of any spacecraft. Spectroscopy tells us what stars are made of. Tiny shifts in starlight reveal planets orbiting suns we will never approach. In this way, the universe invites understanding without requiring presence. That invitation is subtle but consistent. The farther away something is, the more it must be known indirectly. The universe rewards patience, inference, and interpretation. It does not reward haste. 1 light-year is the first distance where this lesson becomes unavoidable. Closer than that, within our solar system, physical travel makes sense. We can send probes. We can imagine people walking on other worlds. The timescales are long but manageable. The environments are harsh but reachable. Beyond that boundary, the logic flips. Travel becomes inefficient. Observation becomes powerful. Presence yields diminishing returns. This suggests that our place in the universe may not be as travellers between stars, but as interpreters of them. There is humility in this realization, but not defeat. Humility does not mean insignificance. It means alignment. It means understanding where effort is best spent and where limits should be respected. Humans are exceptionally good at building models. We compress vast complexity into mathematics, simulations, and stories. We can reconstruct the life cycle of stars we will never touch. We can map galaxies millions of light years away. We can infer the presence of black holes by their gravitational effects alone. None of this requires crossing a light year. In fact, the farther away the universe extends, the more our tools of understanding outperform our tools of movement. This is not accidental. It reflects a deeper asymmetry built into reality. Information travels easily, matter does not. Light carries enormous amounts of information with very little energy. A single photon can tell us about the temperature, composition, motion, and history of its source. It crosses interstellar space effortlessly, indifferent to distance. Matter, by contrast, is heavy. It resists acceleration. It demands energy. It interacts with hazards. It degrades over time. The universe seems optimized for signaling, not for shipping. When we see it this way, 1 light year stops being a frustration and starts being a guidepost. It marks the point where the universe nudges us away from physical expansion and toward intellectual reach. This has implications for how we think about progress. Technological advancement is often imagined as increased mobility, faster vehicles, longer journeys, broader physical presence. But perhaps progress at cosmic scales looks different. Perhaps it means deeper understanding of the environment we already occupy. Consider how much of the universe we already know without leaving Earth. We know the age of the universe to remarkable precision. We know the basic processes that power stars. We know how galaxies form and evolve. We have detected planets around other stars and begun to analyze their atmospheres. All of this knowledge crossed the distance to us at the speed of light, carried by photons that required no fuel, no maintenance, no life support. 1 light year reinforces the idea that knowledge scales better than bodies. This does not diminish the human desire to explore physically. That desire is rooted in curiosity, courage, and identity, but it places it in context. Exploration has always been shaped by environment. Humans explored oceans because oceans could be crossed. We explored continents because land allowed migration. We explore space near Earth because physics permits it with tolerable cost. Beyond that, the environment changes, and with it, the form exploration must take. Accepting this is not surrender, it is adaptation. There is also a cultural lesson embedded here. Human history is filled with expansion narratives. We move outward, we occupy new territory, we settle, build, and claim. These stories are powerful, but they are also specific to Earth's geography. The cosmos does not offer territory in the same way. Stars are not empty lands waiting to be inhabited. They are isolated systems separated by distances that resist colonization. The language of expansion does not translate cleanly to this environment. Perhaps the universe invites a different narrative, one centered on stewardship rather than spread, on understanding rather than occupation, on connection through light rather than through movement. This perspective alters how we think about extraterrestrial life as well. If interstellar travel is difficult for us, it is likely difficult for others too. Advanced civilizations, if they exist, may be similarly constrained. They may observe rather than visit. They may communicate indirectly, if at all. They may be widespread in time, but isolated in space. This makes the universe feel quieter, not because life is rare, but because distance enforces separation. 1 light year thus becomes a filter. It separates local interaction from distant awareness. It allows information to pass while keeping societies apart. In that sense, the universe may be full of life that never meets. This is not a pessimistic view. It is a realistic one. Life does not need contact to have meaning. It does not need to spread endlessly to be significant. It can flourish locally while remaining aware of a much larger context. Earth is already an example of this. Our planet hosts an astonishing diversity of life, most of which will never leave it. That does not diminish its richness. It enhances it. Perhaps civilizations, like ecosystems, are meant to be deep rather than wide. 1 light year encourages that depth. It also reframes ambition. Instead of measuring success by how far we can travel, we might measure it by how well we understand where we are, how sustainably we live, how wisely we use energy, how clearly we perceive our cosmic situation. Civilization that understands its limits is not weak, it is stable. The difficulty of crossing a light year may protect young civilizations from self-destruction. Expansion at planetary scale already strains resources and ethics. Expansion at interstellar scale would magnify those strains enormously. Distance enforces patience. It forces civilizations to mature locally before reaching outward. If they ever do, there is another quieter lesson. 1 light year reminds us that we are temporary, but the universe is not. Stars live for billions of years. Galaxies evolve slowly. Distances that frustrate us are trivial on cosmic timescales. From the universe's perspective, waiting 1 million years for a probe to arrive is not unreasonable. From a human perspective, it is unimaginable. This mismatch tells us something important. We are time-bound creatures in a time-rich cosmos. Our goals, values, and projects must fit within that constraint. We cannot expect the universe to bend to our lifespans. Instead, we learn to work within them. This may explain why human curiosity expresses itself so strongly through science. Science allows us to extend our understanding across timescales we cannot experience directly. We reconstruct the past, we predict the future, we model processes that unfold over billions of years. We cannot live those spans, but we can comprehend them. That may be our niche. 1 light year stands as a boundary between what can be lived and what can be known. We can know across it easily. We struggle to live across it at all. This boundary does not diminish the wonder of the universe. It enhances it. It reminds us that we are participants, not masters. When we look up at the night sky, we are not looking at destinations so much as stories. Each point of light is a history unfolding independently, governed by the same laws but separated by space and time. Our relationship to those stars is observational, not migratory, and that is enough. Understanding this can be comforting. It relieves the pressure to conquer distance. It allows appreciation without possession. It frames exploration as learning rather than claiming. In a way, one light year gives us permission to stay, to focus on Earth, to value the rare combination of conditions that support complex life, to recognize that our planet is not a stepping stone, but a home. This does not mean we stop looking outward. Quite the opposite. It means we look outward with clarity, curiosity, and respect for scale. We listen to the universe rather than trying to outrun it. If interstellar travel remains impractical, what does that mean for human ambition here and now? How do we reconcile our curiosity with our constraints? How do we explore meaningfully without crossing vast distances? Consider a different kind of movement, not outward through space, but inward through understanding, not engines firing, but questions unfolding. When physical travel reaches its limits, something else expands to take its place. This is not a consolation prize. It is a continuation of a pattern humans have followed many times before. Long before oceans were crossed, people explored through stories. Before microscopes, they explored through inference. Before satellites, they explored the sky with mathematics. Again and again, when direct access was unavailable, the mind stepped in. Staying home while reaching farther with our minds is not a retreat from exploration. It is a shift in method. Human cognition is remarkably well suited to this shift. We are pattern-seeking organisms. We compress experience into models. We extrapolate beyond what we can see. We imagine scenarios that have never occurred and test them against logic and evidence. This ability allows us to reach across distances that bodies cannot cross. Astronomy is the clearest example. Every star you see in the night sky is already far away. Even the closest ones are years removed from the present moment. When you look up, you're not seeing where things are, you're seeing where they were, and yet that delay does not prevent understanding. We measure stellar motion, we infer mass from gravitational effects, we reconstruct stellar life cycles from populations at different stages, we read chemical signatures from light alone. None of this requires proximity. In fact, proximity would often make it harder. Stars are too hot to approach. Black holes cannot be visited safely. Supernovae destroy anything nearby. Distance is not a barrier to knowledge here. It is a prerequisite. The same pattern repeats across scales. Cosmology studies the largest structures in existence without ever touching them. Particle physics studies entities too small to observe directly by interpreting traces and probabilities. Evolutionary biology reconstructs deep history from fragments and patterns. Human understanding thrives in indirect spaces. This matters because it reframes what reaching farther actually means. Physical travel extends presence. Cognitive exploration extends comprehension. Presence is limited by energy and fragility. Comprehension is limited mainly by creativity, rigor, and patience. Those are limits that move. Every generation inherits better tools for thinking, more precise instruments, larger data sets, faster computation, shared global knowledge. Each of these extends mental reach without moving bodies. Telescopes are a perfect illustration. Early telescopes showed points of light. Modern ones resolve galaxies. Space-based observatories detect wavelengths blocked by Earth's atmosphere. Interferometry combines signals from distant instruments to simulate enormous apertures. We now see farther than any spacecraft has ever travelled, and we do so continuously, safely and sustainably. The same applies to probes. Sending machines rather than people allows reach without risk to life. Probes can be small, specialised and numerous. They extend sensors, not societies. They bring back information rather than demand new habitats. This is not a second-best option. It is an efficient one. Consider what has already been accomplished. We have mapped planets around other stars. We have measured atmospheric compositions light years away. We have detected gravitational waves from colliding black holes billions of light years distant. We have observed the cosmic microwave background, a relic from the early universe. None of this required leaving Earth. It required careful observation, clever interpretation, and sustained curiosity. Staying home does not mean standing still. It means building deeper foundations. There is also a practical aspect to this approach. Resources invested in understanding tend to produce compounding returns. Better theories inform better experiments. Better experiments refine theories. Tools improve, knowledge accumulates. Resources invested in physical expansion often face diminishing returns. Each additional kilometre costs more energy. Each additional hazard increases risk. Each new environment demands adaptation. From a long-term perspective, mental expansion scales better. This does not imply that physical exploration should stop entirely. Local exploration remains valuable. Studying nearby worlds helps us understand planetary processes, potential habitability, and our own origins. Exploring the solar system deepens context. But beyond that neighbourhood, the cost-benefit balance shifts. Staying home allows focus on Earth itself. Our planet is not a trivial backdrop. It is a complex dynamic system with deep interconnections. Climate, geology, biology, and human society interact in ways that are still not fully understood. Understanding Earth better may be more urgent than understanding distant stars. From space, Earth appears fragile, a thin atmosphere, a narrow temperature range, delicate balances that support life. These conditions are rare and precious. Reaching farther with our minds includes turning them back toward home, studying climate systems, understanding ecosystems, modelling long-term environmental change, developing sustainable technologies. These efforts also require imagination, rigour, and patience. They are forms of exploration no less challenging than interstellar travel. In a sense, Earth is the most alien world we inhabit because we are part of it. Understanding a system from within is harder than observing from without. Staying home also supports continuity. Knowledge built on Earth can be shared, preserved, and refined. Institutions can collaborate. Errors can be corrected. Progress can be cumulative. Long interstellar missions break continuity. Feedback arrives too late. Context changes. Lessons cannot be applied quickly. Mental exploration thrives on feedback loops. This aligns well with human timescales. We can test hypotheses within years or decades. We can revise models. We can teach new generations. Progress remains connected to lived experience. This connection matters for motivation and meaning. Exploration that yields understanding within a human lifetime sustains engagement. Exploration that spans centuries risks becoming abstract, disconnected from those who initiate it. Staying home keeps exploration human-scaled. There is also an ethical dimension. Physical expansion often carries unintended consequences. On Earth, exploration and colonization brought exploitation, displacement, and environmental damage. These outcomes were not always intentional, but they followed patterns of resource extraction and dominance. Projecting these patterns onto interstellar space may be premature, but it's not irrelevant. Expanding physically without deep understanding can magnify harm. Mental exploration emphasizes observation over intervention. It encourages learning before acting. This mindset may be better suited to a universe where we are not the central actors. Another important aspect is inclusivity. Mental exploration is more accessible. It does not require selection into elite crews or massive infrastructure. It allows broader participation. Education, communication, and collaboration can involve millions rather than dozens. Science thrives when many minds contribute. Interstellar travel by humans would, by necessity, involve very few people. Mental exploration involves many. This difference shapes culture. A civilization focused on understanding rather than expansion may value education, critical thinking, and cooperation more highly. It may invest in long-term knowledge rather than short-term conquest. That cultural shift could be as significant as any technological one. Reaching farther with our minds also reshapes how we think about time. Instead of racing toward distant destinations, we learn to think across deep time. We study cosmic evolution. We model future scenarios. We consider long-term consequences. This temporal expansion complements spatial limits. We may not cross light years easily, but we can span billions of years in understanding. That is not trivial. Few species have ever done that. There is also a quieter benefit. Staying home reduces risk. Interstellar travel would expose humans to hazards we barely understand. Failures would be irreversible. Losses would be final. Mental exploration carries lower stakes. Errors cost time and resources, not lives. Hypotheses can be wrong. Models can fail. Learning continues. This risk profile matters. A civilization that survives long enough to understand the universe deeply must avoid self-destructive ventures. Prudence is not fear. It is foresight. This does not extinguish wonder. In many ways, it enhances it. When you accept that you will not stand beneath another star, you may look more closely at the one you have. When you accept that other worlds remain distant, you may appreciate the rare conditions that allow you to ask questions at all. Wonder does not require ownership. It requires attention. Reaching farther with our minds also prepares for futures we cannot predict. Perhaps technology will change. Perhaps new energy sources will be discovered. Perhaps methods we cannot imagine now will make interstellar travel more practical. If that happens, it will be grounded in understanding built beforehand. Knowledge is the seed of capability. Staying home does not close doors. It keeps them unlocked. It allows readiness without recklessness. There is a personal dimension to this as well. Each individual life is finite. No one will see humanity cross a light year. But anyone can participate in understanding the universe. Reading, learning, questioning, teaching. These are accessible forms of exploration. They offer connection to something larger without requiring escape from where you are. In that sense, mental exploration is deeply human. It meets us where we live. This perspective also softens disappointment. If you let go of the expectation that humanity must spread physically to be meaningful, the universe feels less forbidding. Vast distances stop being barriers and start being context. They tell us what kind of beings we are. We are not conquerors of space. We are interpreters of it. That role is not lesser. It is fitting. Our tools reflect this. Telescopes, detectors, computers, theories. They extend perception, not muscles. Our achievements reflect it too. Maps of galaxies, models of cosmic inflation, predictions confirmed by observation. These are quiet triumphs, but they are real. Staying home also allows continuity of culture. Art, philosophy, ethics, and meaning develop in stable environments. Constant migration disrupts continuity. Long-term reflection requires settled contexts. A civilization focused inward can mature. This does not mean isolation. Communication across the planet and beyond continues. Information flows. Collaboration spans cultures. But the physical anchor remains. Earth remains the reference point. That anchor provides stability. As we learn more about the universe, we also learn more about ourselves, our limitations, our strengths, our place. One light year helped teach that lesson by refusing to be crossed easily. It forced a reassessment of ambition. Now that reassessment turns into orientation. If we stay, how do we stay well? If we observe, how do we observe wisely? If we learn, how do we use what we learn responsibly? These questions matter more than propulsion equations. They guide decisions that affect generations. Slowly, attention returns from the vast scales just considered to something smaller, quieter, and more immediate. After thinking about distances that stretch beyond intuition, energy budgets that dwarf civilizations, and timescales that erase individual lives, there is a natural pullback toward the present moment. Not because the universe has become less interesting, but because perspective has done its work. Earth comes back into view. Not as a dot in a photograph, not as a metaphor, but as a place where gravity still holds your body gently in place, where air fills your lungs without effort, where time passes at a pace your nervous system understands. After all the reasons we cannot cross even 1 light year, this return is not a disappointment. It is a grounding. Drifting back to Earth does not mean abandoning curiosity. It means situating it. From here, the universe looks different than it did when the journey began. The stars no longer feel like destinations waiting just beyond reach. They feel like companions at a respectful distance, present through light, influence and context rather than proximity. That shift matters. Human imagination often leaps outward first. We dream of leaving, of moving on, of expanding endlessly. Those dreams have driven remarkable achievements. They have also sometimes distracted from what was already fragile and valuable close at hand. Thinking carefully about why we cannot travel even 1 light year brings that value into sharper focus. Earth is not merely where we started. It is where the conditions for asking questions exist at all. Stable temperatures, liquid water, a protective atmosphere, a magnetic field that deflects radiation, a biosphere that cycles nutrients and moderates extremes. These are not guaranteed features of planets. They are rare combinations that took billions of years to emerge. The difficulty of leaving highlights how finely tuned this environment is to us. Every obstacle discussed earlier, radiation, energy, biology, time, becomes trivial when viewed through the lens of daily life here. On Earth, radiation is filtered. Energy arrives through ecosystems and infrastructure. Biology evolved in sync with gravity and climate. Time passes at a pace that allows generations to overlap, share knowledge, and build culture. None of this required engineering. It was given. That does not mean it is indestructible. Understanding how hard it is to survive elsewhere underscores how easy it is to take survival here for granted. Earth feels robust because it has always worked, but that robustness depends on balances that can be disrupted. Atmospheric composition, climate regulation, biodiversity, fresh water cycles. These are systems we live inside, not systems we control. The realization that we are effectively confined to this planet, at least for the foreseeable future, reframes responsibility. There is no backup world waiting a light year away. There is no realistic evacuation plan. There is no easy migration path for billions of people. Staying home is not a choice, it is a condition, and conditions invite care. Drifting back to Earth also means returning to human timescales, days, years, lifetimes. These are the units in which meaning is made. Even the most ambitious scientific projects are organized around them. Careers span decades, institutions span centuries at most. Interstellar timescales overwhelm that structure. Earth-based ones support it. When curiosity is aligned with lived time, it becomes sustainable. When ambition stretches too far beyond it, meaning thins. This is one reason why learning about the universe feels satisfying even without travel. The act of understanding fits within a human life. You can look at the sky, read, think, discuss, and slowly build a picture that deepens over years. That process itself becomes a journey. It is not passive. It requires effort, discipline, and humility. It demands that assumptions be revised and that ignorance be acknowledged. It rewards patience. These are qualities that also support life on Earth. There is a subtle symmetry here. The same traits that make science effective, careful observation, skepticism, long-term thinking, are the traits needed to care for a planet. Quick fixes, unchecked expansion, and short-term gains undermine both understanding and sustainability. One light year, by being so difficult to cross, nudges us toward these traits. It discourages impulsive expansion. It encourages reflection. This does not mean humanity will never leave Earth physically in more ambitious ways. It means that such steps, if they occur, will emerge from long periods of stability, understanding, and restraint rather than urgency or escape. Escape is a dangerous motivation. When people imagine fleeing Earth for distant stars, it often reflects dissatisfaction with present conditions. Environmental stress, social conflict, uncertainty about the future. But distance does not solve those problems, it magnifies them. The physics that make interstellar travel difficult also make planetary neglect irreversible. If we damage Earth badly enough, there is nowhere else to go in a practical sense. This is not meant as alarmism, it is an observation grounded in scale. Drifting back to Earth, here and now, invites a different emotional response. Not fear, but appreciation. Appreciation for gravity that keeps oceans in place. For an atmosphere thick enough to breathe but thin enough to let light through. For ecosystems that recycle waste effortlessly, something no spacecraft can do indefinitely. Even the inconveniences of Earth, weather, seasons, aging, are signs of a dynamic system that supports complexity. From the perspective of interstellar space, Earth is astonishingly generous. This generosity extends to culture. Human societies are imperfect, but they are rich. Language, art, music, humour, shared memory. These emerge from proximity, from frequent interaction, from overlapping lives. A generation ship would struggle to maintain that richness. A suspended crew would pause it entirely. A robotic probe would not experience it at all. Earth sustains it naturally. Returning attention here also means returning to the body. After thinking about how fragile human biology is in extreme environments, it becomes easier to appreciate how well it functions in this one. Bones remodel in response to gravity. Muscles strengthen through movement. Immune systems train against a manageable background of microbes. Even pain has context here. It signals injury in an environment where healing is possible. Sleep follows a rhythm synchronized with daylight. Hormones cycle predictably. Development unfolds within known parameters. These processes are often invisible because they work so well. Interstellar travel exposes how tightly coupled they are to this planet. There is also a psychological grounding that comes from recognizing limits. Limits can feel constraining, but they also reduce anxiety. When everything is possible, expectations inflate. When boundaries are clear, priorities sharpen. Knowing that humanity is not about to scatter across the galaxy simplifies certain questions. It focuses attention on this world, this century, these people. It does not diminish wonder. It localizes it. The night sky becomes less of a map of future colonies and more of a reminder of context. Each star marks a different system, unfolding independently, connected to us by physics but not by proximity. That separation does not make them irrelevant. It makes them humbling. Humility is often misunderstood as weakness. In this context, it is alignment with reality. Aligned curiosity is powerful. It leads to careful science, to cautious engineering, to policies that consider long-term consequences, to cultures that value continuity. Drifting back to Earth also restores scale to individual lives. Against the backdrop of light years and cosmic timescales, personal concerns can feel small, but that does not make them unimportant. It places them in a framework where meaning is created locally. Relationships matter because they occur here. Creativity matters because it is shared here. Care matters because this is where it has effect. The universe does not ask us to be everywhere. It asks us to be attentive where we are. This attentiveness can extend outward through observation, imagination, and learning, but its anchor remains. That anchor is not static. Earth changes. Climates shift, societies evolve, knowledge grows. Staying grounded does not mean staying the same. It means evolving within limits rather than trying to outrun them. There is a quiet relief in this. The pressure to achieve interstellar reach can feel like a test of worth, as if a civilization that does not spread is incomplete. Letting go of that test opens space for different measures of success: resilience, wisdom, sustainability, understanding. These are not consolation prizes, they are achievements in their own right. As attention settles back into the present, the initial question feels different than it did at the beginning. Why can't humans travel even 1 light year? The answer is no longer frustrating, it feels explanatory. We cannot because we are shaped for a different role, because the universe favours information over migration, because energy, biology and time set boundaries that encourage depth over spread, and because Earth already provides what long voyages struggle to recreate. This does not close curiosity, it steadies it. From here, future questions arise naturally. How do we observe better? How do we understand more deeply? How do we care more wisely for the environment that makes understanding possible? Those questions do not require engines or fuel. They require attention, cooperation and patience. They can be pursued tonight, from wherever you are, under whatever sky you happen to see. As thoughts settle, the scale of the universe remains vast, but it no longer presses outward. It surrounds gently, offering context rather than challenge. The stars keep their distance, Earth keeps its hold. And within that balance, there is room to breathe, to wonder, and to rest, knowing that even without crossing a light year, the universe is already very close.